Welcome, friend. Settle into a comfortable position. Let your shoulders drop a little. The night is patient, and so are we. We are going to follow a quiet visitor across the dark, not to chase headlines, but to listen for what color can teach us about where things come from and where they're going. You are a calm observer on a slow voyage. Imagine the faint hum of a ship that never rocks, with windows that look out onto star fields, arranged like scattered salt. You do not need to steer. You're here to notice how the heavens breathe when they are undisturbed. So, before our journey begins, take a moment to like the video and subscribe, but only if you feel a genuine connection to the mysteries we explore here. Or, if you feel comfortable, tell us in the comments where you're listening from and what time it is. The community stretches from midnight kitchens to morning trains, from cities to quiet fields. Now, dim the lights. Let the world outside fade away, and let's drift into the cosmos together. Look out across the dark and imagine a whisper of green, no brighter than mist at the edge of dawn. Astronomers have given the visitor a simple name. They call it 3IATLAS, a placeholder of letters and numbers that says more about the order in which it arrived than the story it carries. It is not a harbinger. It is a teacher. Color is its chalkboard. The green is not a warning flare. It is chemistry waking up. When a cold traveler moves closer to the sun, ices at its surface begin to breathe. That breath forms a thin atmosphere around it, a coma that can glow in certain shades. Among the most common is a soft green born from dicarbon, a molecule with two carbon atoms bonded together. When sunlight energizes these pairs, they sing near the middle of the visible spectrum and paint the coma with a sea glass tint. Cyanide can also play its small, sharp part, showing up in the blue-violet, a spectral neighbor that says the chemistry is lively but not dangerous at our distance. Here's a compact bundle of numbers for your mind to hold and then set down. The swan bands of dicarbon glow near 520 to 560 nanometers. The green your eye is sensitive to. The coma can span many thousands of miles, though most of its brightness is close to the nucleus. Photons from the sun pump energy into those molecules, and in a matter of hours to days, sunlight breaks some of them apart, so the green rarely stretches far down the tail. The visitor's projected pass keeps it roughly 200 million miles from Earth, which in celestial terms is a generous cushion. You can relax your jaw. Picture 3IATLAS as a quiet ember in motion. It is likely only a few miles across, perhaps smaller. Wrapped in a cloud, you could pass through without noticing if you are a rock. The glow is not a solid thing. It is the statistical sum of countless collisions and the rhythm of electrons falling back into lower energy states. It is science that loves large numbers and long patience. What matters about the green is what it implies. For the color to bloom, carbon has to be present in a form that sunlight can untangle. That suggests a birth environment where simple carbon compounds were available to freeze into the body long ago. Interstellar objects that wander into our neighborhood are time capsules. 1I and 2I showed us the diversity already. One looked like a dry shard that tumbled oddly. The other behaved like a more familiar comet, with a straightforward coma and tail. Our new visitor's hue adds another page to that slowly growing book. You might ask whether a toxic word like cyanide should make us uneasy. In space, scale and dilution soften the edges of worry. The amount released by a small traveler in a thin coma disperses quickly. Earth is far outside any meaningful stream. Even in our own atmosphere, we are shielded by wind, gravity, and distance. The numbers do not just reassure. They explain why astronomers sleep well between observations. Imagine standing on a quiet hill before sunrise. The air is cool. You are looking for a color you cannot quite name. The green appears like the memory of a leaf. It is not bright enough to pull you out of yourself. It is gentle enough to let you stay where you are, attentive and at peace. That is how to watch a comet. The eye sees, the mind slows, the heart steadies. There is also a practical joy to this. Color helps us decode. If dicarbon dominates, we learn that parent molecules in the object are likely breaking into those pairs under sunlight. If cyanide is strong, we learn about a different carbon pathway. If both are present in familiar proportions, we file that pattern next to dozens of comets from our own system. If the ratios are unusual, we start to ask what kind of nursery could have set those recipes long ago around another star. A gentle speculation for you to keep or let go. Perhaps 3IATLAS wandered for millions of years through interstellar cold, its surface baked by radiation into a thin crust that kept its inner ices quiet. Only the slow increase in sunlight as it approached our star let the gases escape, changing the object from a dark stone to a lantern. If so, the green would be a sign of hibernation ending, rather than something strange or threatening. What can a shade of green tell us about a place it has left behind by countless light years and countless winters of dust and dark? Maybe just this, that carbon is patient, that simple molecules travel well, that the building blocks of more complicated chemistry do not belong to any one system or one sun. They roam, they arrive, they glow for a while and keep going. Our task in this voyage is to notice the difference between a signal and a story we tell about the signal. The green is a signal. It says there's carbon. It says there's sunlight. It says there's motion. The story we tell will be careful and kind. We will use it to understand origins and to place worry where it belongs, far away on a shelf labeled with long timescales and generous distances. For now, let the image linger. A small traveler, a soft green, the sky still dark around it. You do not have to reach for anything. The night is doing the holding. The chemistry is doing the speaking. We are here to listen. The room is still. Imagine the faintest wash of color over dark glass. The kind that asks for a second look rather than a second thought. Green in space is not paint. It is light filtered through molecules that have been awakened by the sun. When a cold object grows warm enough, buried ices begin to lift off as gas. That gas builds a thin, temporary atmosphere around the nucleus that astronomers call a coma. Inside that cloud, specific molecules can glow when sunlight tickles their electrons and then lets them fall back to calmer states. The result is a color that looks alive, even though it is only physics, expressed in a soft hue. Dicarbon is often the quiet hero here. Two carbon atoms bonded together can radiate near the center of your visible range when they are energized by sunlight. The effect is strongest in the coma and fades quickly down any tail. Cyanide, a small and reactive molecule, also glows, but it prefers the violet end of the spectrum and can ride a little farther from the nucleus. Both signals are familiar to comet observers, like no notes in a piece of music that changes with distance from the sun. You can picture the coma as a lake of light that is deepest near its center. The green lives near the surface where gas is thick enough and the photons are plentiful. Farther away, sunlight has already broken apart many of the glowing molecules. That is why photographs sometimes show a green head that does not carry the same color far into the tail. The chemistry is local and short-lived, renewed by the steady breath of escape from sunlit ice. Here's a compact bundle of numbers to hold and then release. The swan bands of dicarbon cluster around 520 to 560 nanometers. Emission from cyanide is strongest near 388 nanometers. At a sun distance of roughly 1 astronomical unit, many dicarbon molecules survive for hours, while cyanide can persist a little longer in the thinner parts of the coma. Typical gas production for a modest comet may reach a few hundred pounds per second as it warms. Yet the density remains so low that a person moving through the cloud would feel nothing at all. The visible coma can span tens of thousands of miles, but most of the brightness sits within the inner few thousand. Two hard facts help us translate color into composition. First, we know from laboratory spectra and decades of comet observations that dicarbon is a common secondary product created when sunlight breaks larger organic molecules apart. Second, we know that cyanide, often traced through the CN fragment, tracks a different lineage that can point to native ices or quickly processed organics. Measuring these features across a range of distances from the sun lets astronomers tell parent molecules from their photochemical children. That leads to a small grounded speculation. If 3IATLAS shows a strong and compact green head with only a faint violet fringe, it may be rich in parent compounds that break into dicarbon near the surface, while cyanide either forms less efficiently or is rapidly destroyed close in. If the violet signature grows stronger farther from the nucleus, then cyanide could be forming or surviving better in the outer coma. Either way, the pattern sketches a map from sunlight to chemistry in a language we have learned to read with some confidence. There is also the question of dust. Fine grains can scatter sunlight and change how our eyes read the scene. If the coma holds many very small, bright particles, they can enhance the green by providing a luminous backdrop that makes emission lines seem fuller. If the grains are larger or darker, the glow may appear muted, even when the molecules are present in healthy amounts. This is why observers chase both images and spectra. Pictures tell us where the light goes. Spectra tell us why it shines. Think for a moment about what green means under your sky at home. Fresh leaves, shallow water over pale sand, old glass in a window. In a comet, it means energy moving through a simple molecule, and that molecule is a messenger for origins. Carbon chemistry does not start here. It starts wherever the object was assembled long ago, in a nursery, under another star, or in a cold outer shelf of matter that drifted free. The color carries memory without needing to remember. Another hard fact anchors the calm. Color does not imply danger. The presence of dicarbon or cyanide in a sparse coma is not a hazard across the gulf of space. At Earth's distance, any outflow from a small traveler dilutes into near nothing before it could affect us. This is why green is an invitation to study, not a signal to worry. Astronomers care about ratios and lifetimes, not alarms. A gentle question follows. If color is a map, what else might it mark about the birthplace of 3IATLAS? Could a higher ratio of dicarbon to cyanide hint at an environment rich in complex organics that were heavily processed by radiation before the object escaped its home? Might a modest cyanide signal point to ices that formed farther from a young star, where ultraviolet light was kinder and nitrogen chemistry slow? We will carry those questions forward and let new data decide how far to trust them. For now, it is enough to understand that green in space is a chemistry lesson written in light. Sunlight energizes. Molecules answer. The coma becomes a classroom with no walls. The tail, a chalk line that fades as it extends. Every color invites the same kind of listening. We look with our eyes, measure with our instruments, and let patience turn brightness into knowledge. If you step back from the specific wavelengths and lifetimes, you can feel how simple the story is. Carbon travels well. Sunlight is a gentle catalyst at these distances. A small object warms, breathes, glows, and then quiets. The glow helps us place the object on a map of possibilities. It tells us which recipes might have been used to assemble it, and which ovens of starlight cured those ingredients over long ages. Hold the image of a quiet green resting near a small, dark nucleus. The signal will strengthen and soften as the sun angle changes. It will speak more during approach, then whisper as the object recedes. We will listen throughout, not for drama, but for the patient details that make a new visitor feel familiar. The first photographs arrive quiet, as postcards from a misty shore. A round, pale head, a hint of sea glass color close in. Nothing dramatic, just the soft announcement of chemistry starting to breathe. Early images of a new visitor rarely settle the story. They sketch it through wide fields and narrow filters. Observers see a compact halo, perhaps a little asymmetry, and a color that seems to thicken near the center. The green is not a blanket. It is a shallow pond of light where molecules are most freshly made and most easily excited. Beyond that small lake, color gives way to the ordinary scatter of dust. In these first nights, instruments speak a language that patient minds translate. Unprocessed frames look gray. Calibrated frames reveal signatures. Narrowband filters isolate the familiar notes of carbon species. Broadband filters capture the continuum that dust reflects. Together, they let us separate glow from glare. A few careful exposures under steady air show a round head with a slight gradient toward the sun, like a candle's halo pushed gently to one side by an invisible breeze. Here is a compact bundle of numbers to hold and then let go. With seeing near 1 arcsecond and a pixel scale around half an arcsecond, a small telescope resolves structures a few thousand miles wide when the comet sits at roughly 1 astronomical unit. The coma's surface brightness often follows a 1/ρ trend, dimming with distance from the center. A modest dust production can produce an AFR of a few hundred centimeters, while gas lines from dicarbon sit near 530 nanometers and cyanide near 388 nanometers. Phase angles of 20 to 30 degrees add a gentle reddening to the dust continuum, while emission lines remain anchored by physics, not geometry. 2 hard facts help us read these sketches correctly. First, the green we notice in photographs comes primarily from dicarbon, which forms when sunlight and time split larger organics into smaller pairs that radiate strongly near the center of the visible band. That glow is short-lived and tends to hug the nucleus. Second, the overall color of the coma is a combination of emission and reflected sunlight from dust, and that dust usually shows a slight red slope. Separating the two requires spectra, or carefully chosen filters, that keep the lines and the continuum from talking over each other. The first puzzle is often about proportion. How much of what we see comes from gas, and how much from dust. A coma rich in fine grains can look brighter and smoother, adding a soft white that dilutes the green without erasing it. A gas-lean scene may still feature a visible tint, but it will be tight and localized. When observers stack frames and measure profiles, the shape of the light reveals the mix. Steeper profiles whisper gas. Flatter ones nod toward dust. There is also the gentle question of variability. A cold traveler can flicker as it turns, exposing patches where fresh ice reaches sunlight. If one of those patches feeds a jet, the inner coma may brighten on one side. The green thickens there for a while, then relaxes as rotation hides the source. The rhythm of that change tells us about spin and geography without ever resolving the surface itself. A grounded speculation follows from the quiet evidence. If the early green appears compact and steady, 3IATLAS may be turning slowly or presenting a stable face to the sun. If the tint grows asymmetrical or pulses over a few hours, we may be watching a rotating pattern of vents waking up. Neither case is unusual. Both are comfortable within what decades of comets have taught us. The enigma, if any, lives in the ratios, not in the behavior. Consider what a small network of observers contributes on nights like these. Large observatories catch spectra and high-resolution images. Modest backyard telescopes, well-guided and well-calibrated, track brightness changes and coma size from hour to hour. When those curves are pooled, they form a steady hum of data across longitudes and weather. Even a few photographs taken under suburban skies, if timed and processed with care, can confirm whether a brightening is global or local, sustained or fleeting. It helps to picture the geometry. The sun sits off to one side. The visitor breathes most on its sunlit face. Gas expands in all directions, but the freshest, densest region remains close in. Dust drifts outward more slowly, carrying sunlight like chalk dust in a classroom beam. The colors mix near the center and separate farther out. A slight off-center brightening may be nothing more than the simple fact that sunlight is not everywhere at once. There are human puzzles too, the kind that make observers smile rather than fret. Cameras and eyes are eager to please. White balance can lie. Processing can oversaturate. A calm practice keeps the story honest. We measure through the same filters, from night to night. We note the face angle and the air mass. We accept that sometimes the most faithful image is the one that looks less dramatic. Truth in early data is quiet. Two more steady facts support the calm. Interstellar visitors are rare, but the physics they follow near our sun is not. Sublimation thresholds, photochemical pathways, and dust dynamics do not forget themselves because a traveler's passport was stamped in another system, and the distance to Earth is wide. With a separation on the order of hundreds of millions of miles, during these observations, even a lively outgassing is more poetry than peril from where we stand. Hold one vivid image as we end this first look. Imagine a dim pearl with a faint green breath drifting across a field of star pins that do not blink. The pearl is not fragile. It is an old stone carrying a long memory. The breath is not a warning. It is the way sunlight writes on gas for a little while. A gentle, open question lingers as more spectra accumulate and the comet approaches a warmer reach of its path. Will the green thicken and then retreat in the ordinary pattern we know? Or will the ratio sketch a slightly new recipe that adds a small page to the book of carbon under other suns? The night holds steady. Picture a slow curve traced on a blackboard, chalk moving without a sound, showing how a small traveler passes through our neighborhood. and keeps to the polite side of space. When people hear about a visitor that glows, they often ask how close it will come. The answer, for 3IATLAS, is simple and kind. Its path stays well outside any lane that could trouble Earth. Astronomers compute that path with methods that have been tested for more than a century, tuned by radar, optics, and the shared heartbeat of gravity. The result is a set of numbers that let us sleep without rehearsing worries that do not belong to this moment. 2 hard facts anchor the calm. First, the geometry of the passage is set mainly by the sun. Earth is a small player at this distance, unless an object threads a very narrow corridor. Our planet does not have much say in the visitor's course. Second, even modest uncertainties in early measurements shrink quickly as more observations come in. With more nights of data, orbital elements tighten and projected missed distances settle into stable figures that are far larger than anything we experience inside our own orbital neighborhood. Here's a compact bundle of numbers to hold, then release. Think in round values. The closest approach to Earth sits near 200 million miles, about 2/10 of an astronomical unit. Relative speed around this time is on the order of 30 miles per second, which is typical for a small body diving through inner space. The moon is 250,000 miles away, so the pass is roughly 800 lunar distances. At that range, the visitor is a quiet geometry problem, not a hazard. Gravitational tugs by Earth are tiny. Changes in the orbit due to our presence amount to a shift that instruments can detect, but that life cannot feel. Another steady fact applies to comae and tails. A glowing coma looks larger than the solid core, but it is thinner than the best desert air. The gas can span tens of thousands of miles, yet the density is so low that even if a piece of it crossed our path, the molecules would be lost in the spread of our own atmosphere before anyone could name them. Green is a property of light and chemistry near the nucleus, not a halo that can reach across millions of miles to paint our sky. It helps to picture the stage. The sun rests at center. Earth moves along its wide circle. Our visitor follows a loop that slices through the plane of the planets at an angle, a bright needle drawn over a dim record groove. The miss is not a narrow squeak. It is a comfortable margin where small uncertainties can dance without changing the story. This is what astronomers mean when they say the solution is well determined. They are saying that the curve on that quiet blackboard does not drift when you add new chalk marks. A grounded speculation follows from the pattern we see. Interstellar objects arrive with a range of inclinations and speeds. They do not share the tidy, nearly circular paths of native asteroids and comets that evolved in our plane. That means their approach directions and exit directions are often steep, and steep paths usually keep their closest passes farther out from the clustered family of planets. If 3IATLAS fits that familiar interstellar geometry, then the wide miss is not a surprise. It is expected. There is a softer part of distance that matters too, the kind you feel rather than calculate. When the numbers are large and the timescales are long, the mind has room to breathe. You can enjoy the photographs or the thought of the photographs without translating each new image into a measure of risk. This is not the kind of story where a line must end with a warning. It is a story about how far a signal can travel and still be gentle when it reaches you. Two more hard facts make the reassurance complete. The energy that sets the coma glowing is sunlight, not internal heat that hints at violent change. As the object leaves the sun's warm zone, the breathing slows, the glow softens, and the whole scene returns to its quiet baseline. And impact probabilities for any object are computed by agencies that exist for that purpose, with public risk tables that are updated as data improves. In cases like this, those tables remain empty of any line that points to Earth during the current passage. If you like one vivid image, carry this: a small stone with a soft, green breath moving across a great plain. You stand at the far edge of the plain. You can see the stone because the air around it gleams, a polite signal that chemistry is awake. You cannot feel the breeze that carries that breath because the distance is generous. Sight and thought reach farther than touch, which is exactly how we prefer it. Because we are careful, we name what could change. Gravity is a patient artist, and small nudges add up over years, not weeks. If a close pass by a large planet were in the future, that could alter an orbit in ways that would matter, but not on a time scale that affects this approach. For 3IATLAS, no giant hand waits around the corner to twist its path toward us. The drawing on the blackboard stays smooth. A gentle question remains, and it is not about threat. When the pass is complete and the object drifts outward again, what will the record of its brightness, color, and tail shape say about where it has been? Will the green that comforted us also help constrain the temperature history of its surface, the size of its grains, and the mix of simple molecules that woke in sunlight? In other words, can distance teach as much as proximity, just as a soft voice sometimes carries meaning better than a shout? For those who like a final cluster of numbers to set beside the image, here is one to pocket loosely. The escape speed from Earth sits near 7 miles per second. Our visitor moves at several times that, relative to us, at its pass. That means it is not captured, it is not circling in, it is not changing camps to become a local. It is a traveler with its own itinerary. And we are a quiet town. It passes by on a wide road. Let your shoulders drop again. The chalk curve fades on the board. The stone crosses the plain, and the night keeps its promise of peace. Distance, in this case, is a kindness built into the clockwork of the orbits. We are here to notice, to measure, and to remember, not to brace. Think of a glass marble on a windowsill, catching a stripe of sunlight. The color you see is not the marble reaching out to you. It is light playing inside it. Comet green is like that. It is performance, not pursuit. When a comet head glows green, the physics is simple and kind. Sunlight pours into a small cloud of gas around the nucleus. Electrons in certain molecules Take in that energy. Then let it go again as visible light. Dicarbon favors the green your eyes know well. Cyanide contributes mostly in the violet. Both are honest markers of chemistry at work, close to the source. Neither is a sign that anything is reaching across space to touch you. Two hard facts help the mind settle. First, the coma is extraordinarily thin. Even a lively comet releases only a modest mass per second compared to any planetary atmosphere, and that gas expands into a vacuum that erases density. Second, the lifetimes of the glowing molecules are short. Ultraviolet light breaks them apart in hours to days, which keeps most of the green near the head and prevents it from painting the sky far down the tail. Here's a compact bundle of numbers to hold briefly and set down. At about 1 astronomical unit from the sun, typical photochemical lifetimes for dicarbon are on the order of a few hours. Cyanide fragments survive a bit longer, but still not long by human measures. A modest comet might vent a few 100 pounds of gas per second when warmed. Spread over a spherical shell tens of thousands of miles wide, the resulting densities fall far below what your lungs would notice, even if you were there. At Earth's distance of roughly 200 million miles from our visitor, any trace molecules that drift outward are thinner than a thought. Color becomes clearer when we separate the parts. Gas glows. Dust reflects. The green is mostly gas emission, tight to the source. The brighter white, or slightly reddish wash, is sunlight bouncing off fine grains, pushed by radiation pressure into a gentle sweep. Neither signal carries hazard across the gulf. They carry information. One tells you which molecules are excited. The other tells you how many particles ride the light. A grounded speculation follows from these steady pieces. If 3IATLAS shows a compact green head and a dust tail with ordinary slopes, then its activity is likely within the range we have measured in many comets from our own system. That would mean carbon chemistry consistent with familiar photolysis pathways, dust sizes that scatter as expected, and outflow rates that rise and fall with sunlight in a rhythm we can predict. If something diverges, it will appear as a ratio in a spectrum or a timing offset in brightness curves, not as a new kind of risk. There's a difference between toxicity and exposure that is useful here. Cyanide is a word that startles on Earth because in concentrated form, it interferes with biology. In a comet coma at astronomical distances, it is a tracer, not a threat. The amounts are tiny. The path to us is long. The space between is unforgiving to any molecule trying to stay together. By the time that chemistry reaches us, it has been diluted into nothing. Our own atmosphere is a giant filter. Our magnetic field and solar wind shape are additional shields. The numbers do more than soothe. They show why soothing is the appropriate response. Two more hard facts lock the frame in place. The energy for the glow is external, not eruptive. Sunlight drives this choir. Nothing inside is burning. And the geometry of the pass keeps Earth outside any meaningful stream. We are watching from a comfortable distance, like someone listening to a concert across a park. You hear the music. You do not feel the breath of the singer. If you want a vivid image to keep, try this one. You're looking at a small ember in an ocean of dark air. Around it, the air is lit for a while, in a green that feels like old glass. The ember moves on a path that never curves toward you. The light fades behind it as quickly as it brightened ahead. You're left with a memory and a notebook full of measurements, not with anything you need to clean up or brace against. Because we are careful, we also name the edges of the map. Dust trails can intersect planetary orbits long after a comet passes, leaving meteor showers. Those showers are gentle on human scales, grains smaller than a pea burning out high above. Moments of light, not danger on the ground. Gas, for its part, does not linger in coherent streams across hundreds of millions of miles. It is scattered by sunlight, wind from the sun, and the sheer geometry of expansion. One question lifts quietly. If interstellar comets share familiar chemistry near our sun, what differences in their green might point back to very different nurseries? Could a slightly stronger or weaker dicarbon signal, after accounting for dust and distance, hint at how radiation processed organics in the place where 3IATLAS first formed? Might a subtle pattern in cyanide emission suggest a slower or faster path of nitrogen chemistry before this traveler was set free? These are questions of origin, not of safety. Danger, when it belongs in a comet story, comes from mass and trajectory. A large rock on a path that crosses Earth's orbit closely and often is worth tracking with care. A small, gassing traveler at great distance is worth watching for knowledge and beauty. 3IATLAS, with its wide mists and modest signs of activity, lives firmly in the second category. The green is part of that constellation. It signals sunlight and carbon working together across a small space, then falling quiet again as the heat loosens its hold. One more compact cluster of numbers to lay alongside the image. Earth's atmosphere has a mass on the order of 1,000,000,000,000 tons. A typical comet outflow over a day amounts to a fraction of that, expanding into a sphere larger than our planet before it would ever reach us. Even if the chemistry were less friendly, the scale would undo it. Space is wide. Dilution in a vacuum is absolute in a way that is hard to grasp until numbers make it simple. So the rule of green becomes easy to remember. In comets, color is a teacher, not a threat. It draws your attention to a region where electrons are busy and molecules are talking to light. It asks for a spectrum, a profile, a patient notebook of brightness with dates and times. It does not ask for alarm. It does not ask for a vault or a bunker. It asks for the same thing the night asks of you now: to notice, to breathe, to let meaning rise at its own pace. A gentle, open question remains as we close. If color is story, and story is memory made visible, what will this particular shade tell us later about the kitchens of stars where carbon learned to travel? Will the green of 3IATLAS become one more page that makes distant nurseries feel like cousins? Or will it hint at recipes we have not quite written down yet? Before we turn the page, keep the last image for a moment. A small stone with a soft green breath, moving across a great plain. We step closer now, not with our feet, but with finer questions. The glow becomes lines. The lines become ratios. The ratios become a quiet signature we can read. Picture a thin beam of starlight passing through a prism until it becomes a ribbon of colors. Now place the coma of 3IATLAS in that ribbon and let the light write down what it finds. This is spectroscopy, the art of turning glow into handwriting. Every molecule has its favorite notes. When sunlight lifts an electron and the electron settles back, the photon released has a color that fits only certain steps. In the green we care about, the carbon tends to sing in a cluster called the swan bands. In the violet, cyanide leaves a clear trace that observers have leaned on for decades. Dust does not sing in lines. It reflects sunlight with a gentler slope, like a background hum that needs to be separated from the melody. Here is a compact bundle of numbers to hold gently and set down. The strongest dicarbon bands sit between 520 and 560 nanometers. The cyanide feature that observers use most often lives near 388 nanometers. A modest spectrograph on a medium telescope can reach a resolving power around 2000, which is enough to separate bright comet bands from the sunlit continuum. Larger instruments reach 10,000 or more. Typical exposures run from a few minutes to about 20 minutes, depending on brightness and seeing. At a distance of about 1 astronomical unit, the inner few thousand miles of coma dominate the signal in a narrow slit. Two hard facts anchor what the lines mean. First, the green bands of dicarbon are usually not from native C2 ice. They are produced when parent organics are broken by sunlight into smaller fragments that then radiate. That tells us the green is a second-generation signal. Second, the CN feature is sensitive to the presence of nitrogen-bearing parents and to ultraviolet pumping. Its intensity relative to dicarbon gives a clue about the chemical mix that is escaping the surface and how quickly it is being processed. A grounded speculation follows from those anchors. If the spectrum of 3IATLAS shows a strong, compact dicarbon emission with a moderate CN line, then the surface may favor carbon-rich parents that photolyze efficiently near the nucleus, while nitrogen pathways are present but not dominant. If the CN line grows stronger at larger distances from the center, it could mean that some cyanide forms or survives slightly better in the outer coma, shaped by the balance between sunlight, flow speed, and density. We also pay attention to the continuum, the gentle slope from dust. Comet dust is often a little red compared to sunlight, which means it reflects slightly more strongly at longer wavelengths. That slope can dilute the visual impression of green or make it pop, depending on grain sizes and albedo. By fitting and subtracting the continuum, observers recover the true strength of the bands. The result is a set of line fluxes that can be turned into production rates with the help of simple models of how gas expands and is destroyed by light. Think of this as listening in a quiet room. The gas lines are notes on a piano. The dust is the soft hum of air through a vent. You can hear both at once. But if you want to learn the song, you lean closer to the piano and gently hush the vent. The spectrum is that lean. The reduction is that hush. Another hard fact extends our reach. The way line strengths change with distance from the nucleus helps separate parent molecules from their children. If a line peaks close in and drops quickly, the emitting species is short-lived or produced near the source. If it rises a little farther out, it may be a child made from a parent that takes time to break. By moving the slit outward from the center, or by using a wider field spectrograph, we can map these changes and infer lifetimes without ever catching a molecule in a bottle. A practical note fits here. Interstellar visitors can be faint and small. Slits must be placed carefully. Guiding must be steady enough that the nucleus stays on target. The coma is not a solid object. It is a soft gradient. Observers often nod the slit along the tail to sample gas at several offsets and then subtract background sky. A few well-placed positions can turn a single night into a simple radial profile of chemistry. The vivid image to hold is this. Imagine a black page sprinkled with tiny stars. Across the page runs a bright thread, the comet's light split by glass. On the thread, green hills rise where dicarbon speaks. A violet mound marks cyanide. Between them lies a pale, sloping plain from dust. You're not just looking at a picture. You're reading a heartbeat. One more compact cluster of numbers helps frame the calm. Flow speeds in an inner coma are often a few thousand feet per second. Photochemical lifetimes for dicarbon, near 1 astronomical unit, are a few hours. For cyanide fragments, they can be a bit longer. Taken together, those values suggest that the brightest green should sit within a few thousand miles of the nucleus and soften quickly as the gas is torn apart by ultraviolet light. That is why the green head can look tight, while the tail looks more neutral. A gentle, open question follows. Will 3IATLAS show ratios that fall comfortably inside the family we know from our own comets? Or will one of the lines sit a little higher or lower than expected after dust subtraction and geometry are accounted for? If it does, will that difference point back to a cooler nursery where certain parents froze out more quickly, or to a warmer one where radiation hardened the surface and changed which molecules could escape? There is dry humor in the work too, the kind that keeps observers grounded. Spectra do not gossip. They tell you exactly what you asked in the language you chose. If a calibration lamp goes dim or a flat field is old, the answer will be wrong but consistent. Patience and repetition are the cures. You do not argue with the lines. You tune your instrument and return the next clear night. 2 more steady facts quietly reassure. First, None of these lines implies hazard at distance. They are tracers of composition, not messengers of harm. Second, the same physics that shapes green in native comets shapes green in interstellar ones. The origin story may change with ratios, but the nearby behavior remains familiar. Sunlight lifts, electrons settle, photons depart on paths that end in our telescopes. If you close your eyes now, you can still see the thread with its small hills. You can imagine the room where observers lean over a monitor, quietly satisfied when the bands emerge from the noise. This is how a color becomes a fingerprint, not with drama, but with a ribbon of light and a table of values that add up to meaning. Imagine a frost-dark pebble turning slowly in a sunbeam. Where light lingers, a thin breath rises. Where shadow returns, the breath pauses. The visitor is not waking by itself. The sun is the quiet hand on the dimmer. When cold surfaces warm, the most volatile ices begin to leave, molecule by molecule. The process is sublimation, a direct step from solid to gas that needs only heat and a free path to space. Gas pushes outward, drags fine dust, and makes a temporary atmosphere that thickens on the sunward face. This is the source of the green glow. The color is a byproduct of sunlight moving through a cloud that sunlight created. Two hard facts set the frame. First, sublimation acts like a thermostat. As soon as an ice begins to escape, latent heat is removed from the surface, which limits the temperature rise and stabilizes the outflow. Second, activity is controlled by illumination and geometry. A small shift in the angle of sunlight, a ridge that hides a patch of frost, or a slow spin that moves a bright stripe across the surface can modulate the gas. The coma responds within minutes to hours, not days. Here's a compact bundle of numbers to hold and then release. The solar energy flux at Earth's distance is about 1,160 watts per square meter. A sunlit patch of dirty ice can settle near a few hundred kelvins, depending on how quickly it radiates and how strongly it vents. Water ice begins to sublimate vigorously once surface temperatures climb past about 170 kelvins. Typical gas speeds in the inner coma are a few thousand feet per second. The thermal skin depth that feels a diurnal cycle is measured in inches, so only the uppermost layer rides the day and night rhythm. Photochemical lifetimes for green-making dicarbon are on the order of a few hours near this distance, which confines the color near the head. The choreography is simple and beautiful. Sunlight arrives, warms a thin layer, and frees gas. The gas expands and cools. Electrons in molecules absorb photons and then fall back down, shedding light in the green where dicarbon is present. Cyanide can contribute in the violet with its own rhythm and reach. Dust lifted by the gas or loosened by cracks scatters sunlight to form the soft continuum. What we see is a dialogue between heat, flow, and light. One grounded speculation follows from this. Physics. If 3IATLAS shows green that rises and falls gently over a rotation, without sharp spikes. Its active areas may be broad and smooth rather than narrow jets. If, instead, the inner coma shows slight asymmetries that repeat on a steady cadence, vents could be localized, perhaps at the foot of scarps where sunlight pools longer. In either case, the driver is the same. The sun writes the schedule, the surface reads it, and the coma answers in color. Consider texture. A crust exposed to cosmic rays over long drifting years can become compact. Beneath it, ices remain ready. When warmth cracks the skin, gas escapes along fissures and finds daylight. Fine grains may be cemented by organics that soften with heat. That softening encourages dust release just as the gas peaks, which thickens the near-field haze and makes the green look richer by giving the emission lines a soft backdrop. Two more steady facts keep the calm honest. The chemistry is externally powered and therefore self-limiting as distance grows. When the visitor begins to recede, the same energy that opened the pores diminishes, the outflow slackens, and the coma relaxes. Also, the pattern of green does not imply any new kind of radiation or unusual spectrum beyond what comets have shown for decades. Interstellar origin can change ratios and textures, but not the basic script that sunlight uses near our star. For a moment, picture the day on the nucleus. Morning is a low-angle warm-up. Noon is a narrow band of deeper heat that walks across the face. Evening is a soft glide into shadow. The coma breathes with that day. The green thickens in late morning on the sunward side, stays steady through the hours of peak light, then thins as shadow returns. If the body turns slowly, the changes are broad and unhurried. If it turns more quickly, the inner coma can pulse with a dignity that feels like a slow tide. Because we are careful, we ask what might complicate the pattern. A jet that pierces the crust could extend the region of strongest green a little past the subsolar point. A patch of unusually dark material could heat faster and vent more strongly, then cool quickly and fade. If the surface is dustier than expected, it can insulate the ice and delay the start of activity, which would make the onset of green feel sudden at a certain distance from the sun. There is a practical humor in how the equations behave. The same physics that gives a neat curve in a classroom sometimes gives messier curves in the sky, simply because real surfaces are patchy. Observers accept this without complaint. The solution is not to wish for a sphere, but to keep watching until repetition reveals the underlying clock. Underneath the quirks, sunlight keeps time. One vivid image for your pocket. Imagine a ring of faint steam rising from a cup left in a beam of afternoon light. The steam is invisible until the beam cuts across it. Where the light meets it, you see a column. Where the light misses, the column seems to disappear. The coma is that steam, and the green is the part of the column that catches the beam in just the right way for your eye to notice. A gentle, open question remains. As 3IATLAS moves deeper into warmth and then out again, will its light curve, color ratios, and inner gradients point to a surface dominated by broad, mellow sources? Or will we find a few bright veins feeding most of the flow? If we can match those patterns to simple thermal models, we will have turned a shade of green into a map of where heat gets work done on a small, ancient stone. Imagine a thistle puff in slow motion. The seeds drift outward from a small heart. Some fall into a curve that sunlight shapes. Some are carried straight away by a wind you cannot see. Around the heart hangs a soft halo that seems to breathe. This is the simple choreography of a comet's head, its dust tail, and its more delicate ion tail. Each part keeps time with the sun. Two hard facts anchor the picture. First, the coma is a thin, roughly spherical cloud that forms when ices turn to gas and expand from the sunlit side. Close to the nucleus, density is highest, and the green from dicarbon is easiest to excite. Brightness there often follows a 1/over distance profile, dimming as molecules spread. Second, tails are direction keepers. The dust tail curves gently along the orbit because sunlight pushes grains while gravity draws them, creating a soft sweep. The ion tail points almost directly away from the sun, shaped by the solar wind and magnetic fields, often straight and faintly blue. Here's a compact bundle of numbers to hold for a moment, and then let go. Gas near the nucleus often flows outward at around 1 mile per second. Fine dust leaves more slowly, a few 100 feet per second at first, then drifts under radiation pressure. Typical dust grains that shine well in sunlight can measure microns across. The ion tail often shows emissions from molecules that lost electrons, such as CO+, glowing in the blue near 420 to 440 nanometers. The green dicarbon bands live between 520 and 560 nanometers and stay tight to the head because photochemical lifetimes are only a few hours near Earth's distance from the sun. Timing is the quiet metronome. As illumination increases, outgassing strengthens. The coma thickens. The dust tail brightens as it is fed. Lines in the spectrum grow until photolysis and expansion balance the supply. Around perihelion, when the sun's warmth peaks, the whole system reaches its calm maximum. Then, as distance grows again, the flow relaxes. The ion tail fades quickly because it depends directly on fresh gas and the solar wind. The dust tail lingers a little longer along the path, like chalk dust slowly settling. One grounded speculation follows from this simple clock. If 3IATLAS behaves like many modest comets, we will see the green coma grow more concentrated and slightly brighter as it approaches its nearest point to the sun, and then soften afterward. The dust tail may lengthen and show a gentle curvature that records several weeks of outflow. The ion tail, if present, could appear as a thin, almost needle-like extension away from the sun on nights when the solar wind favors strong fluorescence. None of this implies unusual activity. It is the ordinary rhythm of heat applied to ice and dust in a patient vacuum. Consider geometry for a moment. The sun sits to one side. The nucleus rotates, presenting fresh patches to light. Gas launches in all directions, but is densest sunward. The dust tail leans back, slightly curved, tracing a compromise between solar push and orbital motion. The ion tail stands like a compass needle, an anti-sun line that may kink or ripple when the wind changes. Because dicarbon is short-lived, the green halo is most intense in the inner few thousand miles, and often does not carry down the dust tail. This is why photographs often show a green head that fades to a more neutral tail. Two more hard facts keep the scene honest. The continuum you see in the tail is reflected sunlight from grains, not glowing gas. Its color can be slightly red compared to the sun's light because of how small particles scatter. And the coma's inner brightness profile often tells you whether gas or dust dominates. A steeper falloff near the core hints at gas. A flatter one suggests dust. Observers use that shape, along with narrow filters, to untangle the contributions without touching a single grain. There is texture inside the flow. Jets can sculpt the inner coma into subtle fans. As the body turns, a fan may swing, briefly feeding one side of the dust tail more strongly. Even then, the outer tail keeps its larger logic. Radiation pressure sorts grains by size. The tiniest depart, fastest, and curve more. Slightly larger ones lag, creating a layered sweep. Over a few weeks, the layers record time, like tree rings written in light. Think of a single vivid image to carry. A small lamp in fog. Close to the lamp, the fog is green, a shallow lake of color that feels alive. Farther out, the fog becomes pale and bends into a slow arc. Off to one side, a thin, straight thread runs away from the lamp, almost invisible unless you look closely. The lamp never brightens to pain. It swells and relaxes with the day. The room remains kind. Because we are careful, we ask what could complicate the timing. A fresh fracture can spike activity for a short period, deepening the green and puffing the dust tail before the system settles again. A crossing of a solar wind boundary can tease the ion tail into kinks or temporary disconnections that look dramatic in photos, but are commonplace in the physics of charged particles. If the nucleus rotates with a period of several hours, you might see small pulses in the inner coma as vents face the sun, then roll away. Here's a second compact cluster of numbers that sets the scale of patience. Solar radiation pressure is strong compared to gravity for micron grains, giving effective accelerations that can reach a few thousandths of Earth's gravity. That is enough to bend the dust tail gently over days. Ion tails respond in minutes to changes in the wind. The total visible length of a dust tail can reach millions of miles, but the part that looks crisp in a small telescope is often measured in a fraction of that, depending on sky darkness and phase angle. A gentle, open question lingers. In the layered sweep of the dust tail and the tight glow of the green head, can we read the turning of 3IATLAS like a clock? Will small asymmetries repeat on a steady period that hints at how the body spins? And if they do, will the pattern tell us whether a broad field of sources feeds the coma, or whether a few patient vents do most of the work, humming along in sunlight as they have for a very long time? In the end, coma, tail, and timing are three parts of a single soft machine. Heat opens pores, gas escapes, dust follows. Light writes in green and white and faint blue. The handwriting changes with angle and hour, but the alphabet stays the same. We are here to read it slowly, not for alarm, but for the pleasure of recognizing a familiar script written by a visitor from far away. Hold an image of three travelers set on a dark shelf. One is a shard that tumbled oddly. One, a classic dusty snowball. And one, a small lantern with a hint of green. They're cousins, only by the fact that they passed our porch. Two hard facts give the comparison a steady floor. The first interstellar visitor, 1E Oumuamua, crossed the inner system in late 2017 with no persistent coma. A strange light curve that implied an elongated or flattened body a few hundred meters across, and a small, non-gravitational push, best explained by gentle outgassing or the sublimation of a volatile skin. The second, Tuoy Borisov, discovered in 2019, behaved like a conventional comet with a nucleus roughly a kilometer wide, a visible coma and tail, and spectra rich in familiar molecules and dust. Both arrived on hyperbolic paths, their speeds near tens of miles per second relative to the sun, their inclinations steep compared to the calm plane of our planets. Here's a compact bundle of numbers to hold and then set down. Oumuamua's aspect ratio was likely greater than 6:1, with a brightness variation that swung every 8 hours or so. Borisov's dust production placed it within the range of small solar system comets. Its coma spanning tens of thousands of miles, near perihelion. Each approached within a few 100 million miles of Earth, and then departed, uncaptured. Their hyperbolic excess speeds, the measure of how much faster than escape they traveled, sat around 20 to 30 miles per second, enough to guarantee that they were guests, not migrants. Against that backdrop, 3IATLAS presents itself less as a surprise than as a third data point. A faint green halo near the head suggests that sunlight is breaking parent organics into dicarbon close to the nucleus, the way many comets do. A comfortable missed distance of about 200 million miles keeps the conversation in the realm of chemistry and light, not hazard. If spectra show a measured CN feature alongside the swan bands, the family resemblance grows clearer. The differences will live not in the basics of coma and tail, but in the ratios and rhythms. Think of the three as a small progression. Oumuamua posed the puzzle of a dry traveler with an odd shape and a whisper of force that nudged its path. Borisov restored the familiar picture, a venting nucleus, dust and gas in balance, a composition that matched our catalog with a few fresh notes. 3IATLAS, with its soft green, offers a calm middle ground. Not inert like the first, not unusually dusty like some outbursts in the second, but active in a way that turns color into a gentle teacher. A grounded speculation slips in here. If 3IATLAS sits closer to Borisov in behavior, visible gas, ordinary dust slopes, and emission lines that rise and fall with sunlight, then the chemistry of planet-forming regions beyond our sun may be less exotic and more continuous than we once guessed. It would mean that carbon pathways leading to dicarbon and cyanide are common outcomes in cold nurseries, no matter which star anchors them. The puzzle would then shift from asking whether interstellar comets are different to asking how their small difference in ratios map back to temperature, radiation, and time in their birthplaces. Another paired fact steadies the comparison. Interstellar objects are not subject to the long sculpting that ties many native comets to Jupiter or to the Kuiper Belt. They are ejected early, probably by gravitational nudges in crowded young systems, then sandblasted by cosmic rays for long, quiet ages. That suggests a crust that can be tough, a surface that may delay outgassing until warmth, and cracks align. When activity starts, the green head tight to the nucleus makes sense. It reflects very local chemistry, waking under the same sun, that teaches our own comets to speak. Picture a single, vivid scene to hold them together. 3 marks on a chalk line. The first, a thin dash that does not smear. The second, a soft stroke that feathers into a tail. The third, a small dot with a green edge that brightens and dims as the chalk moves under a lamp. None touches the earth mark on the line. All pass with polite distance, leaving us with notebooks, spectra, and a growing sense that the galaxy shares recipes. Because we are careful, we acknowledge the edges of what we know and what we infer. Oumuamua's exact shape and composition remain debated because we never saw a coma and never split its light into clear lines. Borisov gave us genuine spectra and dust, so its chemistry is better pinned. 3IATLAS will belong to the second class if its emissions remain measurable, a visitor that lets us turn color into numbers and numbers into gentle conclusions about origin. 2 more hard facts, and then a question. First, green in 3IATLAS does not imply anything unearthly in the sense of danger. It implies carbon fragments lit by sunlight in a thin local cloud. Second, the comparisons we draw sharpen because the physics near the sun is the same for all 3. Illumination, sublimation, flow, and photolysis repeat their steps. The variations emerge from what the travelers bring with them. The gentle, open question. When we add 3IATLAS to the short list, do we start to see a spectrum of interstellar visitors that spans dry shards to classic comets with only modest gaps? Or will some future 4I present a composition that bends the family curve in a new direction. If the family is continuous, our sky will become a quiet census of other systems' kitchens. If it is not, each new green, gray, or blue-tinged traveler will be a reminder that not all nurseries tell the same story with the same colors. For now, let the three marks linger. A shard, a snowball, a green-edged ember. Together, they say that interstellar space does not only carry rocks, it carries context. Each pass adds a line to a slow, reassuring paragraph about how planets and comets are made anywhere there's dust, ice, and time. Picture a quiet hillside at night. One dome turns like a slow watch. Its slit a narrow pupil. A smaller tripod nearby hums softly as it follows an invisible path. Both point toward the same faint smudge, and both, in their own ways, make the smudge speak. Large observatories and backyard rigs share the same task. They turn light into numbers that can be trusted. The big mirrors gather many more photons. The small ones gather time and patience. When a visitor like 3IATLAS drifts in, the two communities knit a single tapestry. Wide eyes find it. Precise instruments take its measure. Neighborhood observers hold the thread on cloudy nights. For the big sights, half a world away. Two hard facts set the floor. First, the heart of the measurement is not the picture, it is the calibration. Without flat fields to even the frame, dark frames to subtract the camera's own whisper, and a catalog of standard stars to nail down brightness and color, a lovely image is only a postcard. Second, motion control matters as much as optics. Comets do not sit still against the stars. Non-sidereal tracking that matches the comet's drift keeps the nucleus on the same pixels and the green head sharp enough to resolve the inner gradients where chemistry is loudest. Here is a compact bundle of numbers to hold and then let go. A medium research telescope with a mirror about 4 meters across can reach faint features in exposures of 10 to 20 minutes, delivering resolutions around 2000 with a basic spectrograph and about 10,000 with a high-resolution setup. A good backyard telescope with an 8 to 12-inch mirror and a cooled camera can reach the comet's inner coma to magnitude 16 or so in stacked exposures, totaling 30 to 60 minutes, with a pixel scale near half an arcsecond under steady air. Narrowband filters centered near 530 nanometers isolate dicarbon. A violet filter near 388 nanometers samples cyanide fragments. Broadband R or I frames capture the dust continuum that rides behind everything else. The workflow is simple when written and careful when done. Big mirrors split light to read the bands. They place a narrow slit across the inner coma, then step it outward to watch how lines fade with distance. They subtract a modeled continuum to leave only gas. From those cleaned lines, they compute production rates in round numbers that say how many molecules per second are being made and destroyed by sunlight. Meanwhile, the small rigs collect deep images night after night. They measure the coma's size, the tail length, and the brightness within fixed apertures. They plot those values against time. The lines on those plots are the calm heartbeat of a traveler warming and cooling under a predictable star. A grounded speculation follows from this quiet division of labor. If 3IATLAS continues to glow with a compact green head and a modest dust tail, the big scopes will return dicarbon and cyanide fluxes that sit comfortably within the family of small comets, while the backyard networks will show smooth brightening toward perihelion and a gentle fade after. If an outburst occurs, the community will see it together. Spectra will show a brief spike in gas. Light curves will climb faster than the trend and then relax. The map of chemistry and timing will match the physics we expect rather than hint at something strange. Think for a moment about how a spectrum is actually caught. The slit is a thin rectangle placed with care across a moving target. Guiding keeps the comet centered. A comparison lamp, often neon or argon, flashes before or after the comet so that wavelengths fall exactly where they should on the detector. A spectrophotometric standard star is observed to correct for the instrument's own color. Clouds ruin this work. Thin haze can fake a slope. That is why observers speak in quiet tones about a photometric night. It means the sky played fair, and the numbers can carry weight. Now think about small telescopes and the art of stacking. A single 2-minute exposure might barely show a coma and a hint of green, but 50 of those, aligned on the comet's motion and averaged, become a smooth picture with a clean profile. Aperture photometry then measures the light within circles of fixed radius around the nucleus. Subtracting the sky and comparing the result to nearby catalogued stars yields a brightness that can be repeated and trusted. Done nightly, the sequence draws a line that is more meaningful than any single hero image could be. 2 more hard facts keep the practice honest. Ion tails are fickle and can vanish in broadband images even when they are present. To see them, observers often use a filter that suppresses continuum and favors the blue bands where ions glow. And the apparent green of a head in a color picture can be amplified or muted by processing choices. That is why narrowband measurements, or spectra, sit at the center of any claim about chemistry. Pretty pictures invite. Lines and profiles decide. There is a small, dry humor that lives in the difference between professional and amateur tools that matters here. A large observatory can squeeze more detail from a single night than a backyard rig can gather in a month. But a backyard rig can watch 30 nights in a row. The big mirror must share its sky with many projects and weather windows. The small glass belongs to its patient owner. In the case of 3IATLAS, where the story is not a flaring hazard, but a gentle chemistry lesson, that long patience is an equal partner to sharp resolution. One vivid image to keep. Imagine a notebook on a wooden desk. On one page, a ribbon of light with small green hills where the swan bands rise. On the next page, a neat plot of brightness, points, climbing, and settling like a shallow tide. Each page has the date and time in careful handwriting. The notebook belongs to a village, not a single observer. It travels from dome to backyard fence and back again. Because we are careful, we also name the limits. A small telescope cannot disassemble the bands into isotope ratios or trace very faint ion features far down the tail. A large telescope can miss a short outburst while the schedule points elsewhere. Satellites like Hubble and James Webb can take exquisite spectra, but only in short windows and only if the target is bright enough. The cure for all these limits is the same. Share data. Keep watch. Let instruments of different scales braid their strengths. Here is a second compact cluster of numbers to set alongside the image. A good comet narrowband set includes filters for CN near 388 nanometers, C2 near 514 to 535 nanometers, C3 near 405 nanometers, and a pair of continuum bands for subtraction. In a small telescope, each filter might need 5 to 10 minutes per frame, repeated a handful of times to average out noise. In a larger instrument, a single 15-minute exposure at moderate resolution can map all those features at once, then be repeated at several offsets to recover lifetimes. The result is a few pages of tables that turn color into rates with uncertainties of a few tens of %, which is enough to decide whether 3IATLAS sits inside the family we know. A gentle, open question remains. When all the notebooks are compared and the spectra stitched, will the ratios of dicarbon to cyanide and the slopes of the dust continuum tell a simple, familiar story? Or will there be a small lean toward one branch of chemistry that hints at a cooler or warmer nursery beyond our sun? If a lean is found, will it repeat in future interstellar visitors, making a pattern? Or will it stand alone as one traveler's private recipe? Telescopes at work are not machines looking for drama. They are instruments of attention. They take a green seen by an eye and turn it into a list of numbers that carry across distance and time. In doing so, they let a quiet visitor like 3IATLAS become more than a passing color. They let it become a sentence in a long, calm paragraph about how small bodies wake under light and what that waking says about where they were made. Before we leave the ribbon of spectra behind, remember the small green hills that rose where the swan bands spoke. They were close to the nucleus, bright for a short time, and then they faded. In this next part, we set those hills on firmer ground. We ask what makes that green so loyal to the inner coma, and what it tells us about the recipes inside 3IATLAS. Imagine holding a shard of bottle glass to sunlight. For a moment, the glass catches a color that seems to live inside it. In a comet's inner coma, the green behaves like that. It is not the nucleus itself. It is a delicate chorus from molecules that wake, sing, and fall quiet again in a narrow neighborhood near the source. Two hard facts steady the scene. First, the green in most comets is dominated by dicarbon, C2, radiating in the swan bands after sunlight lifts and then relaxes electrons. C2 is not believed to be a native ice in bulk. It is a daughter made when larger parent organics, such as acetylene and ethane, are split by ultraviolet light. Second, because C2 is produced and destroyed quickly, its brightest emission hugs the nucleus. It rarely rides far down the tail. That is why the head can look green, while the tail looks pale or slightly red from dust. Here's a compact bundle of numbers to hold and then let go. The strongest swan band features sit between about 510 and 560 nanometers, near the center of your visible range. At a sun distance near 1 astronomical unit, the effective photochemical lifetime for C2 is on the order of a few hours. Flow speeds in the inner coma are roughly a mile per second. So, most of the green glow lives within a few thousand miles of the nucleus. When observers convert line fluxes to production rates with simple Hazer-style models, modest comets often return C2 production that is a small fraction of water by number, commonly at levels of 1 part in hundreds to a few parts in 1,000. If 3IATLAS is green because of dicarbon, the pattern we expect is straightforward. The lines should peak steeply near the center in a narrow slit, fade quickly with distance, and show a ratio to Cn that falls within familiar families of comets once dust continuum is removed. The continuum itself, set by dust, will slope a little to the red, but subtracting it should not erase the band structure. The result is a fingerprint that says, sunlight is teaching the same lesson here that it has taught for decades in our own backyard. A grounded speculation lives in the parents. Dicarbon's voice often implies that acetylene or ethane are present upstream in the chain, even if they are not seen directly in the visible. If 3IATLAS carries those ices beneath a weathered crust, then a shallow layer of heating near perihelion can feed the inner coma with just enough parent molecules for C2 to bloom when photons strike. The green would then be strongest slightly sunward of center, where the supply is fresh. Farther out, the same light that made the dicarbon would break it again, returning the head to neutral tones within a short distance. Think for a moment about texture at the source. Interstellar travelers may carry a thin, radiation-cured skin that delays activity until cracks open. When vents form, gas escapes through narrow paths that widen slowly. If several such paths feed the coma, their plumes can overlap into a round, compact green lake of light. If one dominates, a modest fan might appear. Either way, the geography is small compared to the size of the coma, which is why the green looks smooth in most photographs taken from far away. Two more hard facts keep the calm in place. The presence of dicarbon in a thin coma at hundreds of millions of miles does not translate to hazard. The numbers are tiny, lifetimes are short, and dilution is absolute at this range. And the physics that sets the bands is external. The sun powers the glow. As distance grows, the energy weakens, the outflow relaxes, and the spectrum quiets with it. With one vivid image may help. Imagine a dark cup set in a beam of afternoon light. A wisp rises, and the beam makes it visible. Close to the cup, the wisp is bright and green, as if the light itself were colored. A few inches away, the color is gone. The wisp is still there for a moment. Then the room's air takes it. The comet's head is that lit inch. The tail is the space where the wisp thins and the light returns to white. Because we are careful, we ask what could complicate the read. Dust can make the head look brighter and hide faint structure in the bands if the continuum is not properly modeled. A rotating nucleus can shift the peak of emission slightly as vents face the sun, which may change the ratio of C2 to Cn over a few hours. A small outburst can deepen the bands briefly if a crust fragment breaks to expose fresh ice. None of these possibilities changes the core meaning of a dicarbon-driven green. They add texture to timing, not danger to distance. There is a quiet satisfaction in how C2 helps with origins. Carbon pathways that lead to these bands imply that simple organics formed, froze, and survived long enough to be carried here. If 3IATLAS shows a ratio of C2 to Cn that is a little lower than average after dust correction, it could hint at a cooler or more shielded nursery where nitrogen chemistry lagged. If the ratio is higher, it may point to richer or more processed carbon stocks. Either way, the differences are measured in gentle factors, not orders of magnitude. They guide the mind, they do not bend the sky. A second compact cluster of numbers completes the picture. Typical narrowband filters for C2 center near 514 to 535 nanometers with bandwidths of a few nanometers, while continuum filters on either side help subtract dust. When spectra are taken at resolving powers near 2000 to 10,000, and the swan bands separate cleanly from the sloping continuum. Fitted with standard fluorescence efficiencies, line intensities translate to production rates with uncertainties often near tens of percent. That level of precision is enough to place 3IATLAS in a known taxonomic class of comets by composition if the green is indeed dicarbon. A gentle, open question lingers as we set down the glass. If C2 is the author of the color here, will its cadence match a steady, broad activity pattern? Or will small periodic changes reveal a handful of persistent vents that do most of the work? And if we can time those changes through the life of the green, would the rhythm tell us something simple and satisfying about how heat threads through an old interstellar stone that is only passing through our light for a little while? Think of a thin violet thread stitched just inside the green. It is not loud. It is a clue that nitrogen is awake in the same sunlight that teases carbon to glow. If the color of 3IATLAS owes part of its life to cyanide, then the inner coma is telling us about another branch of simple chemistry that travels well. Two hard facts form the footing. First, the familiar CN band, used by comet observers for decades, lies in the violet near 388 nanometers. It is usually produced when sunlight breaks hydrogen cyanide into fragments that fluoresce, which makes CN a daughter species rather than a native bulk ice. Second, CN tends to survive a little longer than dicarbon in the same radiation field. That often gives the violet signal a slightly wider reach than the tight green of C2, though both hug the nucleus compared to dust. Here's a compact bundle of numbers to hold and then let go. The strongest CN emission sits at about 388 nanometers. In round figures, photochemical lifetimes near Earth's distance from the Sun can be on the order of a day for CN fragments, while C2 often fades on the scale of hours. Inner coma gas flows outward at roughly a mile per second, so CN's peak emission can extend a few thousand to maybe 10,000 miles from the nucleus before ultraviolet light tears it down. In many modest comets, CN production rates are a few parts in 1,000 relative to water by number, though the exact ratio wanders with the surface recipe and the warmth of the day. If the faint edge of color around 3IATLAS includes a contribution from cyanide, a pattern follows. Narrowband measurements should show a clear CN line that rises close to the nucleus, stays present a little farther out than the C2 bands, and maps cleanly onto the distribution expected for a daughter made from HCN. In a simple model, a narrow slit stepped outward will catch a profile that flattens gently compared to C2. Subtracting the dust continuum, which slopes a little to the red, will leave a violet feature that grows and fades with sunlight in a timing that is slightly broader than the green. A grounded speculation lives in what this would imply about origin. Hydrogen cyanide forms and freezes in cold regions of protoplanetary disks. If 3IATLAS carries HCN just beneath a radiation-hardened crust, then morning sunlight at small heliocentric distances could feed CN steadily through the day, with a modest lag as HCN comes free and fragments in the thin air. The CN to C2 ratio, after dust corrections and geometry are sorted out, would then sketch the balance between nitrogen and carbon pathways in the traveler's birthplace. A CN fraction that is a bit stronger than the family average might hint at a nursery with cooler, denser pockets where HCN was favored. A weaker fraction might point to a warmer or more irradiated environment where nitrogen chemistry stalled or where surface processing buried volatile stocks more deeply. Think about texture and timing. The nucleus turns, vents open to the sun, and then roll away. If a handful of fissures feed HCN into the inner coma, the violet line could pulse on a period of several hours, leading or lagging the green by a small phase, depending on how quickly HCN lifts and breaks. In images, the CN signature will not paint the dust tail. It will gather near the head, perhaps with a slight bias toward the sunward side if the primary vents sit under the noon band of light. Two more steady facts keep the calm in view. Cyanide's reputation on Earth belongs to concentrated doses in closed spaces. A comet CN, at a distance of hundreds of millions of miles, is a tracer, not a threat. Dilution in a near vacuum, short lifetimes, and the long road to our atmosphere reduce exposure to effectively nothing. And the energy that powers the band is the same gentle engine as before, sunlight lifting electrons, then letting them fall. One vivid image to hold. Picture a small lantern veiled with fine mist. Close in, the mist glows a spring green where the molecules are freshly made. Just beyond the lantern's edge, a faint violet seam appears, as if night had a border. The seam is thin, slightly wider than the green, and it fades if you step back. That seam is how CN often shows itself. A quiet fringe that confirms nitrogen has a seat at the same table. Because we are careful, we name what can complicate the read. Poor subtraction of the dust continuum can hide or mimic a weak CN line, especially under bright skies, where the violet is easily swallowed. A rotating nucleus can move the center of activity, so a single long exposure might mix phases and blur a clean profile. Solar wind conditions can change the ion environment and alter fluorescence efficiencies slightly. The cures are repetition, calibration with standard stars, and measurements at several offsets from the nucleus. There's a second compact cluster of numbers that turns lines into rates. Observers apply fluorescence efficiencies, the G factors, to convert CN line brightness into molecules per second. At one astronomical unit, those factors sit in well-tabulated ranges. With a moderate resolution spectrum, around 2000, and a set of narrow band filters for cross-checks, production rates can be recovered with uncertainties on the order of tens of percent. That precision is enough to place 3IATLAS along the simple taxonomies that group comets by C2, Cn, and related relatives, and to decide whether its nitrogen branch is ordinary or a little offset. Another quiet strand belongs to isotopes. In several comets, Cn shows nitrogen isotope ratios that differ from Earth's air. We do not need exact figures here to gain the sense of it. The point is that isotope patterns can carry a memory of temperatures and radiation fields in the place where the parents formed. If 3IATLAS is bright enough for such measurements, even a coarse ratio would add a small but meaningful brushstroke to a picture of its nursery. If it is too faint, the broader Cn to C2 balance still speaks softly about origin, without needing isotope detail. The humor here is dry and practical. Cn bands are old friends to comet watchers. They are conspicuous in the violet, but easily muted by a sky that is too bright. On a perfect night, the bands step out crisply. On a hazy night, they hide and make even a trustworthy comet look shy. No drama is implied by either case. It is simply the difference between a whisper in a quiet room and a whisper on a windy porch. Two more hard facts, and then a question. First, if CN is present, it is telling us that 3IATLAS carries or exposes HCN or related parents, which means nitrogen left marks in the ice at birth. Second, the slight difference in survival time between CN and C2 is why the violet can feel a touch more extended than the green close to the head, while both remain far more compact than the dust tail. Neither behavior is unusual. Both belong to the calm script of sunlight and gas. A gentle, open question drifts forward. After dust is subtracted and geometry is tamed, will the CN line in 3IATLAS sit above, below, or squarely on the median line drawn from dozens of comets we know well? If it leans, will that lean agree with a story of a cooler cradle for nitrogen chemistry? Or will it ask us to imagine a surface layered by time, where HCN is trapped more deeply and speaks only when cracks run a little farther than usual? Either answer is soft. Both add meaning without adding worry. The violet thread, if it is there, is not a warning. It is a second voice singing near the green. Together, they turn a single color into a small chord, and the chord into a clue about how a distant kitchen stocked its shelves before this traveler wandered out to meet our light. Imagine a pale lantern inside fog. Every so often, a few sparks seem to glint and vanish, as if the fog briefly learned to shine like wire. Those flashes are not jewels. They are atoms of metal, freed from dust and made to glow by sunlight, a delicate embroidery hidden inside the green. Two hard facts steady the scene. First, trace metals occur in cometary comae at extremely low abundances, yet they are real and measurable. Observers have identified neutral nickel and iron lines in several comets, and even in an interstellar visitor, showing that refractory material can release atoms under gentle solar conditions. Second, sodium is the most conspicuous metal tracer to the eye, seen through the twin sodium D lines that sit near 589 and 590 nanometers. In a few bright comets, it can even form a narrow, separate tail. These emissions diagnose grain physics, not danger. Here is a compact bundle of numbers to hold and then let go. The sodium D lines lie near 589 and 590 nanometers. Radiation pressure accelerates neutral sodium strongly, so a sodium tail can pull away from the dust tail and extend for millions of miles if production is sustained. Nickel and iron lines populate the near ultraviolet and visible in dense forests of weak features. In round terms, inferred metal abundances in the coma can sit at parts per million relative to water or lower. Typical grain temperatures in the sunward inner coma reach a few hundred Kelvin, warm enough for photodesorption and thermal release of surface atoms, but far below the temperatures needed to melt rock. How do metals arrive in the mist? Sunlight does two kinds of work. It warms grains, and it shakes electrons in surface bonds. A tiny fraction of atoms on exposed mineral and organic coated surfaces are knocked free by photons or by the gentle sputter of the solar wind. Frangible dust can also fracture, exposing fresh faces with loosely bound alkalis like sodium and potassium that are more easily liberated. None of this implies a furnace. It is surface chemistry and light, a slow unthreading of a few atoms from a quilt of silicates and carbon. If 3IATLAS carries the usual mix of silicate dust, a grounded speculation follows. Close to the nucleus, inside a region only a few thousand miles across, we may see a faint sodium glow braided into the green of dicarbon. It will likely be subtle, a small enhancement near 589 to 590 nanometers after the dust continuum is subtracted. On exceptionally steady nights, and with careful calibration, observers may also recover weak blends of nickel and iron lines in the near ultraviolet and blue. Their presence would not be a surprise. Their ratios would matter because they hint at the mineralogy of the grains that carried them across interstellar space. Two more hard facts keep the picture honest. Metals in the coma do not travel far as coherent signals. Neutral atoms are quickly ionized by sunlight. Their fluorescence fades on timescales of hours to a day, and radiation pressure quickly reshapes the distribution. And at the scale of hundreds of millions of miles from Earth, the absolute quantities are vanishingly small. These emissions are tracers you measure with spectrographs. They are not substances you could ever sense on your skin from here. The vivid image to keep is simple. Picture a sheet of green-lit fog that looks uniform from across the room. When you step closer, you notice slender threads of gold and steel woven through it. Those threads are sodium, nickel, and iron whispering in narrow lines. They do not change the color of the whole sheet. They reveal how the sheet was woven. Because we are careful, we name what can complicate the read. The sodium D lines sit in a region where reflected sunlight from dust is also bright. So incomplete continuum subtraction can hide or mimic weak emission. City light pollution often glows near these wavelengths as well. For nickel and iron, line forests are dense and low contrast, which means resolution and signal to noise must be high and wavelength calibration precise. Cross-checks with standard stars and multiple nights help separate sky from comet and comet from instrument. A second compact cluster of numbers frames the retrieval. Moderate resolution, around 2000, can separate sodium from the continuum if the comet is bright and the sky is clear. Higher resolution, near 10,000, pulls individual metal lines apart and reduces blending at the cost of more exposure time. In round terms, a clean sodium detection in a modest comet can emerge in total integrations of tens of minutes on a medium telescope, while nickel and iron require longer and darker conditions. Fluorescence efficiencies for these species are tabulated with uncertainties that yield production estimates, often uncertain by a factor of 2. That is enough for pattern recognition and taxonomic placement, not for accounting down to the last atom. Last, What would metals tell us about origin? Sodium correlates with the presence of fresher, more fragile grains, or with coatings that release alkalis easily. Nickel and iron trace the content and weathering of silicates and sulfides that formed in hot regions of a disk and were later mixed outward. If 3IATLAS shows a slightly higher nickel to iron ratio than the median of solar system comets, after careful modeling, it could hint at a dust population altered by a long radiation exposure or by formation conditions that favored certain alloys or sulfides. If the ratio sits squarely on the usual line, that is its own story. It would say that rocky minerals forged near another star's furnace resemble ours closely enough to give the same spectral whisper at the same warmth. There is a small, dry humor in how these atoms behave. A single grain can lose a dusting of sodium and still remain itself. A comet can shed a trace of nickel and iron without any change you would notice in a photograph. Yet to a spectrograph, each atom is a lighthouse. It blinks at a precise color. The instrument writes down the blink, and the blink becomes a clue about a grain that left its nursery when trilobites were still waiting for oceans to appear somewhere else. Two further steady facts end the caution. A sodium tail, when present, is a narrow, camera-friendly structure that often appears only in bright comets. Its absence says little about composition in faint ones, and the detection of metals in 2I shows that interstellar dust can carry and release refractory atoms near our sun without any unusual heating. Interstellar origin changes the passport, not the physics of release under sunlight. A gentle, open question remains, and it belongs to patience. When all the spectra of 3IATLAS are stacked and the faint lines coaxed into clarity, will the metal pattern look comfortably familiar? Or will there be a small lean that nudges our models of grain history in other systems? Will sodium whisper a little louder than we expect for its brightness, hinting at delicate grains that shed easily? Will nickel and iron keep their quiet balance, or tilt by a small factor that points back to a different blend of rocks where this traveler began? Either way, the answer will live in a few narrow hills on a ribbon of light. The green will keep teaching chemistry in broad strokes. The metals will annotate the margin, reminding us that comets are not only gas and ice. They are stone turned to powder, carrying the signatures of heat and mixing from long ago. The fog glows. The threads gleam. Then the fog thins, and the threads go dark again, leaving the lesson written down where we can read it whenever we like. Imagine shaking a snow globe where the flakes are not all the same. Some are as fine as flour and catch every beam. Some are the size of salt and fall in slow arcs. A few are tiny pebbles that drift hardly at all. The look of a comet depends on this hidden mix as much as it does on gas. Two hard facts set the floor. First, comet dust usually follows a size distribution that favors small grains. In round terms, the number of grains often falls as a power of size, with an index near 3 to 4, which means there are many more micron grains than millimeter ones. Second, radiation pressure pushes small grains far more strongly than big ones. A micron grain can feel a solar push comparable to the sun's gravity on it, while a millimeter grain feels only a small fraction of that. The result is a tail that bends and stratifies by size. Here is a compact bundle of numbers to hold and then release. Grains near 1 micron across can launch at a few hundred feet per second and experience a radiation pressure to gravity ratio of roughly a few tenths to about 1, depending on composition. Millimeter grains launch more slowly, often tens of feet per second, and feel ratios near thousands. Typical dust albedos sit near a few tenths. The visible coma inside the inner few thousand miles can be dominated by submicron and micron grains that scatter efficiently, while the longer tail can contain a layered mix that remembers several weeks of release. 2 more hard facts explain color and shape. Small grains scatter blue light less efficiently than red under many realistic mixes, which gives comet dust a slight red slope compared to sunlight. That is why the dust continuum can look warm, even when gas lines in the green and violet are present. Also, forward scattering can brighten a comet when the sun, comet, and observer line up at small phase angles. In those moments, the tail and coma look enhanced, not because production jumped, but because geometry favored the way grains throw light. A grounded speculation follows for 3IATLAS. If the inner head looks softly green, while the outer coma and tail look pale with a faint warm tint, the grain mix is likely heavy in small particles near the nucleus, with a trail of larger grains that lag and curve less. A subtle brightening at small phase angles would then be expected as a simple scattering effect. If, instead, the tail looks unusually gray and straight for its brightness, the mix could be shifted toward larger grains that reflect more neutrally and are less bent by sunlight. Think about how odd grain sizes can nudge the scene. Very fine grains, smaller than a micron, can make the inner coma look smoother and more extended because they ride the gas well and fill space before settling. They also give narrow-band gas images a brighter backdrop that can make green bands feel richer, even when gas rates are ordinary. On the other hand, a surge in larger grains can make the tail appear heavier and longer-lived, since those grains resist radiation pressure and stay near the orbital path like chalk dust that refuses to blow away. There is texture inside release itself. When gas escapes through vents, it carries a preferred grain size that depends on mouth geometry and cohesion. A vent that opens into a broader cavity can feed a fan rich in small grains, while a narrow crack may choke the flow and favor fewer, larger bits that crumble from the edges. Rotation then sweeps these fans into gentle spirals that smear into the tail. The average observer sees only a smooth arc. A careful profile can find the fingerprints of alternating grain classes within it. Here is a second compact cluster of numbers to keep loosely. A common way to summarize dust is with AFER, measured in centimeters. Modest comets, near 1 astronomical unit, can show AFER values from a few hundred to a few thousand centimeters. A slope of the surface brightness that matches a 1/distance trend hints that gas-driven small grains dominate close in. A flatter slope points to large grains and a thicker dust load. Forward scattering enhancements can add a few tenths of a magnitude when phase angles fall below about 30 degrees, a small but noticeable lift. One vivid image to carry. Picture a river seen from a bridge at night. Near the light, tiny ripples sparkle and move quickly. Farther out, heavier, darker water rolls more slowly and keeps its shape. The green lives where the ripples are, a thin skin of light over fresh gas and fine dust. The tail records the slower water, a sweep written by bigger grains keeping their course. Because we are careful, we name what complicates the read. Color, pictures, can mislead if white balance or saturation is off. A bright sky can hide the low contrast edges where large grains linger. Narrowband filters help, but if the continuum is not subtracted well, grain color can mimic or mute gas lines. The cure is to combine methods. Use spectra to set gas strengths. Use profiles to diagnose grain slopes. Use repeated nights to see whether a change is transient or part of a steady recipe. 2 more steady facts keep the calm in frame. Unusual grain sizes do not create danger at distance. They reshape brightness and color, not trajectories. And the mix can evolve gently with sunlight. Early activity may favor very fine grains as surface frost loosens. Later, as pockets are emptied and crust toughens, larger grains can dominate for a while. The sky records these shifts as small changes in tail curvature and coma slope, the way a diary records moods without changing the person who writes. A gentle, open question lingers. When the dust of 3IATLAS is modeled with simple power laws and tested against images and profiles, will the best fit favor a slightly steeper or shallower size index than the median of comets we know? If it leans, will that lean be a stable trait across weeks, hinting at a built-in texture, or will it drift with illumination, telling us that the surface is layered and the vents survey different shelves of grains as sunlight moves? The snow globe settles. Fine flour rides the light. Salt arcs through the beam. Pebbles hold their line. The green near the lamp keeps its calm place as the dust writes a memory of sizes in the slow curve behind. Think of a porch light with a motion sensor that needs just the right nudge. For a long time, nothing happens. Then the beam clicks on, as if the night itself had decided to be seen. Some comets behave that way. A long, calm approach. And then, at a certain warmth, Activity rises, as if a switch had been thrown. Two hard facts anchor the idea. First, different ices wake at different temperatures. Carbon monoxide can sublimate far from the sun. Carbon dioxide wakes closer in. And water ice becomes vigorous only when surfaces warm to roughly 170 kelvins or more. Second, a thin dust mantle can delay everything. Even a layer only inches thick can insulate buried ice so well that outgassing remains subdued until cracks open or heat leaks through more efficiently. The result is an onset that feels sudden, even though it is the natural crossing of a threshold. Here is a compact bundle of numbers to hold briefly. The solar energy flux near Earth's orbit is about 1,360 watts per square meter. A dark, dusty surface can sit at a few hundred kelvins at local noon under that flux, but a porous crust conducts heat poorly. The diurnal skin depth that feels day and night is measured in inches. Latent heat of water sublimation is large, so once venting begins, it acts like a thermostat, holding temperatures near the sublimation point while gas production climbs. Simple thermal models can turn a silent surface into a modest outflow over hours to days after the threshold is crossed. Two more hard facts explain why the switch looks quiet rather than explosive. The energy source is external and steady. There is no internal reservoir waiting to detonate. When a crack opens, the local flow increases. Dust may lift, and the coma brightens. But the system immediately spends energy to turn ice into gas, which tames further heating. The geometry of sunlight and rotation then sets a repeating pattern rather than a runaway. A grounded speculation follows for 3IATLAS. If early images show only a faint haze, and then, near a particular heliocentric distance, the green thickens and the dust tail gathers, the object may be crossing from a regime where carbon monoxide or carbon dioxide whispered to one where water joins the choir. The onset can feel sharp over a week, simply because the surface passed a stable, cold state into a stable, warmer one. In spectra, C2 and CN lines would rise in step with a broader continuum as more dust is lifted. The ratios might change slightly as deeper layers contribute fresh parents. Think about the role of fractures. Radiation and micrometeoroids can toughen a crust over long, wandering years. Thermal stress then opens it along old weaknesses when the sun returns. A vent that starts small may widen until grains clog it, then shift a short distance where pressure finds the next easiest path. This slow migration of sources can make the coma seem to grow from a handful of points into a broad field over a few rotations, the way a trickle becomes several rills across a dry hillside after a light rain. Here is a second, compact cluster of numbers to place beside the picture. Water becomes a dominant gas near 2 astronomical units and inward for many comets, while carbon dioxide can carry activity between about 3 and 2 astronomical units. Carbon monoxide can start even farther, although at very low rates for small bodies. A modest nucleus, only a mile across, can raise gas production by orders of magnitude over a span of a few weeks as it warms. Yet the density in the coma remains far below any breathable level. Photochemical lifetimes remain hours to a day near Earth's distance from the Sun, which keeps green emission tight to the head even when production increases. One vivid image to keep. Picture frost on a window that looks unchanged until the first thin rivulet appears. Then 3 more, then a wider drift of patterns that catch the morning light. The window did not explode into spring. It crossed a boundary and then wrote a story of that crossing in lines that only light could read. Because we are careful, we name what can mimic a switch. A small outburst from a collapsing scarp can brighten a coma for a short time without any change in average solar heating. A favorable phase angle can boost forward scattering and make growth seem faster. Changes in sky quality can alter how deep images reach. The cure is to track with spectra and with calibrated photometry across many nights. Real switches come with changes in gas lines and with the quiet mathematics of thermal models that predict the timing. 2 steady facts bring the calm back into view. Even on its stronger days, an interstellar visitor on a wide, safe pass remains a distant chemistry lesson, not a hazard. And the same sun that turns the switch on will turn it off again with equal gentleness as distance grows. The coma will relax, lines will fade, and dust will settle into a memory along the path. A gentle, open question remains. When the curves of brightness and line strength are laid over simple thermal predictions, will 3IATLAS show a neat threshold that lines up with water during the flow? Or will it draw a softer ramp that hints at a complex crust where carbon dioxide and water take turns leading? If a threshold is clear, will the rotation of the nucleus add a small, reliable tremor to the curve, the way a heart adds a beat to a breath? The porch light looks sudden to a passerby. To the sensor, it is only the moment a number was crossed. In comets, the number is temperature, the sensor is sunlight and porosity, and the light is the green that tells us gas is now part of the day. The story stays unhurried. The switch is quiet by design. Before we leave the close-in chemistry of dicarbon, cyanide, metals, and grains, keep one small image. A wisp lit in a beam, bright near the source, and quiet a short walk away. In the next part, that wisp becomes a breadcrumb trail. We follow its shade of green back toward birthplaces in cold disks, to lessons about how planets gather, and to the gentle arithmetic of risk and memory. Imagine a nursery behind frosted glass. You cannot step inside, but you can read the color of the light that leaks through. The green around 3IATLAS is that light. It does not show the room. It hints at what is on the shelves. 2 hard facts set the foundation. First, green emission in comets is usually driven by dicarbon, which is a daughter made from larger parents, such as acetylene or ethane split by sunlight. That means the signal we see today is a transformation product of organics that formed and froze long ago in a cold region of a protoplanetary disk. Second, the relative brightness of dicarbon to cyanide, after dust is subtracted, acts as a simple composition ratio. Across many comets, families emerge. Some are richer in C2 relative to Cn. Others are poorer. Those families likely reflect the temperatures, radiation fields, and mixing histories in which their parent ices were laid down. Here's a compact bundle of numbers to hold and then release. In round figures, water condenses in disks inward of roughly 3 astronomical units in early epochs as the environment cools. Carbon dioxide dominates beyond a few astronomical units, and carbon monoxide can stay solid far out at tens of astronomical units. Ultraviolet fields in young disks vary by factors of a few to many, which changes how quickly organics are processed at the surface of grains. When a body assembles where carbon-rich volatiles are abundant and radiation is neither too harsh nor too weak, acetylene and ethane can survive to be sealed into ice. Later, near our sun, those parents feed C2 and the familiar green. A grounded speculation follows. If 3IATLAS shows a healthy dicarbon signal with a moderate cyanide line, it may have formed in a region where carbon-bearing ices were common and where nitrogen chemistry was present but not dominant. That points to a band of the natal disk that was cold enough to trap simple organics, but not so cold that nitrogen ices crowded them out, or to a mixing path that brought carbon-rich grains outward while shielding them from extreme radiation. The exact details are beyond a single spectrum, but the lean of the ratios offers a compass direction. 2 more hard facts. Steady that compass. Disk chemistry is not a neat set of rings. Turbulence blends materials across snow lines, and pebble drift moves solids inward, while ices sublime and recondense. The result is a patchwork. Bodies with similar orbits can carry different recipes, and bodies from different zones can share one. Also, isotopic ratios, when measurable, carry deeper memory than simple line strengths. Nitrogen in Cn and carbon in C2 sometimes show values that differ from Earth's air and rocks. Those offsets speak to the temperature and radiation at formation more directly than brightness does. Think of one vivid image: a pantry lined with jars seen through a greenish pane. You cannot read the labels, but you can guess that many jars hold herbs and dried leaves rather than only salt and sugar. The tint is not the meal. It is a clue that the kitchen stocked certain ingredients. Because we are careful, we name what can blur the clue. Dust continuum can hide or exaggerate band strength if it is not modeled well. Changing phase angle can alter apparent slopes. Rotational modulation can tilt ratios across a night if vents differ in recipe. The cures are repetition, narrow filters, and spectra at several offsets from the head so that photochemical lifetimes are accounted for. When that care is taken, the ratios settle into ranges that can be compared fairly to the families we know. Here is a second compact cluster of numbers to frame the inference. Typical C2 to Cn production rate ratios in solar system comets span from less than 1 to a few, with water as the scale setter at 1. In many surveys, typical comets cluster near unity within factors of a few, while depleted ones fall below. If 3IATLAS lands near the center of that spread, it would say that its birthplace, though around another star, shared the broad chemical balance of our own disk's cold shelves. If it leans high or low by a modest factor, it would point to shelves a little richer or poorer in the parents of C2 or Cn. Two additional steady facts keep reassurance close. None of these ratios imply hazard. They tell a story about where and how a traveler formed, not about what it can do across 200 million miles. An interstellar origin does not erase the physics near our sun. Illumination, sublimation, flow, and photolysis behave here as they do for native comets. The green is a diagnostic in our lab, not a wild card on our stage. What might the greens say about time? Cosmic rays and ultraviolet light bake exposed surfaces for long ages in interstellar space, turning the topmost layer into a crust that resists heat for a while. That crust can change which molecules escape first when sunlight returns. If 3IATLAS shows green that rises only after a gentle threshold, we could be watching a crust give way, revealing a near-surface layer where parents of C2 are common. That sequence would hint at a patient drift between stars, followed by a modest awakening. A story our instruments can test by tracking onset, peak, and fall. One gentle, open question remains. When the campaign ends and line ratios are placed on a simple plot beside dozens of comets, will 3IATLAS sit inside the broad cloud of points we know, a quiet endorsement of shared recipes across disks, or will it hover just off the main cluster, suggesting a nursery with a slightly different balance of carbon and nitrogen? If it stands apart, will future interstellar visitors join it to form a new family, or will it remain a solitary note that widens by a little the chord we call typical? Picture a slow workshop where dust grains stick, grow, and drift like snowflakes, learning to become bricks. A green glow around a visitor is not part of the building, but it is a receipt that lists which ingredients were on the shelf when the bricks were made. Two hard facts guide the workshop tour. First, planets start as pebbles. Millimeter to centimeter grains collide and stick in the midplane of a disk, helped by frost that makes them tacky. As they grow, they drift inward and can be trapped at pressure bumps or snow lines where volatiles condense and recondense. Second, those snow lines act like chemical gates. Inside the waterline, grains are drier and less sticky. Beyond it, ice mantles grow, organics accumulate, and sticking becomes easier. The inventory of a comet encodes which gates its material crossed and when. Here's a compact bundle of numbers to hold and set down. In a young, sun-like disk, the water snow line can lie near a few astronomical units early, moving inward as the disk cools. Carbon dioxide's line sits farther out, often several astronomical units beyond water. Carbon monoxide freezes much farther still, tens of astronomical units away in broad terms. Pebbles drift inward on timescales of thousands to tens of thousands of years. Turbulent mixing spreads material across a few astronomical units over similar spans. These motions blend the pantry. Bodies that assemble at one radius can contain parts that were born far away. A grounded speculation follows for 3IATLAS. If its green implies plentiful parents for dicarbon, and its violet thread suggests moderate cyanide, the material may have assembled just beyond the waterline, where organics are common, or farther out with subsequent drift that mixed in nitrogen-bearing ices. The dust behavior, if it favors small grains near the head and a modest tail, would fit with a surface that has seen both ice-driven cohesion and gentle processing, not with an object built in an extreme furnace or a far black shelf alone. Two more hard facts tie comets to planets. Delivery matters. In our own system, small bodies likely ferried part of the volatile inventory to young worlds after the main building finished. The exact fraction is debated, but the point is pedagogical. If disks around other stars build planets under similar rules, interstellar comets become emissaries from those rules. They let us test whether organic-rich pebbles and ices are common currency in the early economy of planet building. Also, isotopic fingerprints, when available, can suggest how many of those emissaries came from colder versus warmer shelves. Think of one vivid image: a workbench with 3 bowls. One bowl holds frost-dusted grains that cling to each other. One holds darker, drier grit. The third is a mix. If you find a finished brick with a greenish cast in the powder left on its surface, when it warms, you know it spent time close to the bowl with frost and organics. Because we are careful, we note what green cannot do alone. It cannot tell us the exact radius of birth. It cannot read out the time when assembly finished. It simply says that carbon-bearing parents were present and close to the surface when sunlight arrived. To sharpen that picture, we pair color with dust slopes, with any metal lines we can retrieve, and with how activity turns on and off. Together, those pieces sketch whether the traveler's top layers match pebbles that formed where sticking was easy and mixing was strong. Here is a second compact cluster of numbers to frame the logic. Pebble accretion can build kilometer-scale bodies in thousands to tens of thousands of years once local traps collect enough drift. Large planetesimals stir and scatter small bodies across tens of astronomical units on million-year timescales. Ejection to interstellar space occurs when growing giants or crowded resonances fling comets away. A visitor like 3IATLAS could have been launched while its home system was still very young, then wandered for tens or hundreds of millions of years before meeting our light. Its surface would record the recipe at launch, not at birth of its star. Two steady facts hold reassurance steady. None of these building lessons change the safe geometry of the current pass. They change only how we interpret the glow, and similarities are as instructive as differences. If 3IATLAS looks chemically ordinary by our standards, that ordinariness is a profound message. It would say that planet kitchens across the galaxy stock the same staples. That is a comforting thought in a night meant for rest. One gentle, open question lingers. When we line up interstellar visitors beside native comets on a plot of simple ratios and dust behaviors, will a broad overlap appear, implying that pebble physics and snowline chemistry repeat themselves star to star? Or will we see a second cloud of points, offset but parallel, suggesting familiar rules with shifted thresholds? Either outcome is soothing. Both make planets feel less like exceptions and more like patient outcomes, wherever disks cool and grains learn to stick. Imagine a breadcrumb that refuses to spoil. It crosses deserts of cold and radio, then softens again when the right light returns. The green in a comet is not that breadcrumb. It is the sign that such crumbs rode inside. Two hard facts keep this chapter on firm ground. First, comets carry a suite of organic compounds, from simple molecules like formaldehyde and methane to more complex species, including amino acid glycine detected in dust from a comet visited by spacecraft. Those finds do not claim life. They claim chemistry that life could use. Second, organics survive irradiation by hiding in ice and crust. Cosmic rays and ultraviolet light process the topmost layer over long ages. But beneath inches to feet of shielding, molecules can persist for millions of years and then be brought back into circulation when a surface cracks and warms. Here's a compact bundle of numbers to hold and then set down. Typical interstellar travel times for small bodies ejected from young systems can span tens to hundreds of millions of years before chance brings them near another star. Penetrating radiation doses over those spans can alter the top centimeters to decimeters of exposed material, turning it into an organics-rich crust that is chemically tougher but still porous. Gas production near the sun lifts dust from that crust in amounts tiny compared to any atmosphere, yet enough for a spectrograph or sample collector to see. In famous cases, amino acids and a zoo of organics have been measured in cometary grains, confirming that simple prebiotic chemistry is a common outcome of cold physics. A grounded speculation follows for 3IATLAS. If its green points to robust carbon pathways, and if any accompanying dust shows the slight red slope typical of organics-coated grains, then its surface may host a familiar mix of simple carbon chains and rings processed by time. That would place the traveler in the same broad tradition as many comets in our own system, where analysis of grains found complex but non-living chemistry waiting quietly for energy to return. Two more hard facts. Keep the story gentle. Delivery is not destiny. The presence of organics delivered by comets to a world does not guarantee biology. It enriches the starting kit for chemistry under the right conditions. And interstellar space is a strict filter. Only material that can endure long exposure without falling apart makes it to new suns. The organics we see are, by definition, the survivors, stable enough to carry their information across great quiet. Think of one vivid image. A tiny amber bead trapped in ice. Light passes through it and turns warm, even though the room is cold. When the ice melts at the edge, a trace of scent escapes that you cannot define but know. That bead is the role organics play in a comet. They do not shine on their own. They color the light and give the gas a chemistry that a spectrum can read. Because we are careful, we do not overinterpret green. Dicarbon is a daughter made by sunlight near our sun. It announces parents, but does not list them by name. To go beyond the hint, we rely on infrared and mass spectrometry when missions permit, and on careful dust color, work from the ground when they do not. Even then, the message stays modest. It says that small, carbon-bearing molecules were present and that the surface has not been stripped to pure rock. Here is a second compact cluster of numbers for perspective. In spacecraft studies of a well-known comet, glycine and other organics were detected in dust at parts per billion to parts per million by mass. In simple terms, that is enough to matter to chemistry on a young world if delivered widely, and not nearly enough to matter to safety at any distance. Sublimation lifetimes for fragile organics near our sun can be short, which is why they are often bound in dust, not free as gas. The dust, warmed and lofted, returns a soft signature in color and a slightly red slope that a careful instrument can see. A small, dry humor lives here. Interstellar travelers are sometimes described as messengers. They arrive without envelopes. Our job is to read the smudges on the paper. Green is one such smudge. It does not contain a diary. It contains a name, like carbon was here. Two more steady facts bring the calm back to the foreground. At hundreds of millions of miles, none of this chemistry reaches us in any meaningful concentration. And the course of a visitor, like 3IATLAS, does not enter any corridor where dust density could do more than seed a few meteor grains somewhere far downstream. The lesson is intellectual. The night remains kind. One gentle, open question rolls forward. When we gather more interstellar visitors into our modest catalog, will their organics appear as uniform as the few we have studied closely? Or will we find that some disks write richer recipes and some write plainer ones, all within the same quiet rules of ice and light? If a pattern emerges, will it align with star type, with disk mass, or with the tempo of planet formation that either traps pebbles early or lets them wander long. The breadcrumb image holds. A small body keeps a record of pantry items through long dark. The green around it is not a crumb. It is the label on the jar that says such crumbs exist. That is enough for tonight. It is a generous hint, and we have learned to read hints well. Picture a wide beach and a small boat far offshore. You can see its lantern. You cannot hear its oars. The math of distance is the tide between you. Two hard facts keep risk in scale. First, geometry rules these encounters. The path of 3IATLAS keeps it roughly 200 million miles from Earth at closest approach. That is about 2/10 of the distance from our planet to the Sun. Small uncertainties in orbital elements shrink to tiny angles with repeated observation and do not erase a margin that large. Second, the stuff that glows is sparse. A coma can look broad, but its density is far below any air we know. Gas is broken by sunlight within hours to a day. Dust grains are tiny and spread along the orbit, not concentrated streams aimed at us. Here is a compact bundle of numbers to hold and let go. The moon is 250,000 miles away. This pass is on the order of 800 times that. Relative speeds for small bodies near the sun are tens of miles per second. At that pace, even a shallow gravitational tug by Earth at that range does not matter to the path. Earth's atmosphere weighs about 1,000,000,000,000 tons. A modest comet vents perhaps tons per second when active, but into a sphere tens of thousands of miles across. By the time any molecule could wander our way, it'll be thinner than a thought and likely broken by light. A grounded speculation follows. If you see a headline that makes green sound like hazard, the odds are that it has confused color with threat. Cyanide and dicarbon are familiar tracers. They are chemistry notes in a far room, not fumes on a doorstep. The presence of a word that startles in a laboratory does not turn distance into exposure in space. Ratios in a spectrum are ratios of light, not warnings. They are invitations to learn, and that is all. Two more hard facts complete the reassurance. Risk tracking for actual impactors is done by agencies with public tables that list probabilities when any exist. Interstellar visitors on wide passes do not appear on those tables in the way near Earth asteroids do. And meteor showers, when dust from comets crosses our path at the right time of year, are light shows high in the sky. Grains smaller than peas burn out harmlessly. They do not deliver chemistry to the ground at concentrations that matter. They deliver awe. One vivid image holds the point. A lighthouse across a bay. You see a greenish tint because mist and glass do something to the beam. You do not feel heat. You do not smell smoke. You are not in the beam. You're on your own shore, watching a color carry a message about glass and fog, not about you. Because we are careful, we say what numbers would break the calm if they were present. A massive body with a projected missed distance measured in Earth radii would deserve attention. A non-gravitational acceleration that drew the path inward by many Earth radii per week would be unusual. None of those are in play here. The chalk line on the blackboard has been drawn and redrawn by data, and the curve stays wide of our place. Here's a second compact cluster of numbers to pocket. Escape speed from Earth near the surface is about 7 miles per second. The visitor's relative speed is higher, which means it is unbound. It will not settle into our neighborhood. Photochemical lifetimes that shape green are ours. By the time any gas could drift, the green makers are gone. Radiation pressure accelerates micron dust at thousandths of a G. That accelerates curves in tails over days, not arcs across millions of miles toward us. Two steady facts return the tone to rest. The safe outcome is not luck. It is geometry that we can see and compute. And the lesson we extract does not ask us to worry. It asks us to attend. If we do, we leave with a better map of how small bodies speak under light, which in turn feeds our models of how disks and planets grow. Knowledge is the only thing this green delivers in quantity. One gentle, open question remains. Can we teach this arithmetic of reassurance more broadly, so that the next time a visitor glows a benign shade, attention follows curiosity rather than alarm? If a slow tide of calm learning moves across the shoreline of public talk, the night will feel wider and kinder for more people. And that would be a lovely side effect of watching a color do its quiet work. Imagine a drawer full of old postcards, each with a small wash of pale green on the stamp. Different skies, different years. The shade is the same lesson repeating. Comet watchers keep such drawers in their minds and notebooks. Two hard facts frame the collection. First, many comets in our own system show green heads near perihelion when dicarbon blooms in the inner coma. Photographs from decades of apparitions record the pattern. The heads glow near the nucleus. The dust tails stretch pale, and the color fades with distance. Second, when spectra are taken, the same swan bands and CN features recur. With ratios that fall into the families observers have charted since narrow filters became standard tools. The consistency is not boring. It is the definition of a reliable teacher. Here is a compact bundle of numbers to set beside the postcards. For modest comets, C2 to CN ratios often sit near unity within factors of a few, with depleted comets falling below that and typical ones near the middle. AFR values for dust, used as a proxy for production, land in the hundreds to thousands of centimeters for many small bodies near 1 astronomical unit. Ion tails, when present, carry blue emissions that point away from the sun like thin compass needles. The green rarely paints those needles because the emitting molecules are too short-lived to travel far. A grounded speculation links the drawer to 3IATLAS. If this interstellar visitor settles into the same ranges, it will slip into the drawer, as a familiar page with an unfamiliar postmark. The comfort of that would be large. It would say that the physics of disks and the budgeting of carbon are cousins across stars. If instead one or two ratios lean to the edge of the cloud of past comets, then the new card will sit near the corner of the drawer and make future cards easier to classify when they arrive. Two more hard facts remind us how memory improves maps. Repetition shrinks uncertainty. The first interstellar visitor forced us to infer much from little because no coma was seen. The second gave a textbook pattern of gas and dust that was easy to place. A third that glows green in step with sunlight lets us stitch the two together. We learn not only from the exotic, we learn from the ordinary standing next to the odd. Think of one vivid image to close this section. A set of photographs clipped to a line. In each, a small head sits with a green halo and a pale sweep to one side. The stars in the background are different. The years stamped in ink are not the same. The feeling is similar. A quiet lantern at the center, a thin lake of color near it, a curve that remembers weeks of dust. Because we are careful, we do not let nostalgia write the script. Each apparition has its quirks. Some show sodium tails. Some show jets that mark a slow spin. Some bloom a little earlier or later. The only mistake is to imagine that repetition erases the need for measurement. It does the opposite. It rewards it. The more cards in the drawer, the more confident we are when a new one arrives that an odd shade is a hint, not a hoax, and that a familiar shade still deserves a line of numbers and a date. Here's a second compact cluster of numbers that honors the archives. Exposure times for narrowband C2 images in small telescopes often run from 5 to 10 minutes per frame, repeated several times per night to tame noise. Spectra at moderate resolution, around 2,000 to 5,000 resolve bands, well enough for production rates. Photometric sequences over a month can track brightness, changes of less than a magnitude, and connect them to geometry. These are modest demands. They are the reason the drawer is thick. Two steady facts leave the memory with its quiet shine. Green never meant danger in these postcards. It meant sunlight written on gas. And the act of remembering in astronomy is not sentiment. It is signal processing. When a third interstellar page files itself next to two older ones, the composite says more than anyone could. It fixes a point in a growing constellation of evidence. A gentle, open question lingers for the next chapter. How will this particular card age? Will we look back and say that 3IATLAS was the moment we stopped thinking of interstellar comets as rare events and started thinking of them as occasional letters from a wider neighborhood, each written in a hand we can now read without raising our voice or our pulse? Before we open the final pages, think of the drawer of old comet postcards we just browsed, each with a pale green stamp. We will add one more card soon. As 3IATLAS leans toward the sun. Colors may deepen, shapes may sharpen, then everything will soften again. What approaches is not a cliff, it is a gentle crest, the calm high tide of warmth and light. Picture a slow dimmer turning toward its brightest setting and then easing back. That is the rhythm of a small traveler nearing perihelion. The closer 3IATLAS draws to the sun, the more the skin warms, the more ices breathe, and the more the thin atmosphere near the nucleus writes its brief lesson in green. Two hard facts set the stage. First, activity tends to peak near perihelion because sunlight is strongest there, yet the maximum brightness need not fall exactly on the closest point. Thermal lag and rotation can shift the crest by a few days to a couple of weeks. Second, brightness can grow not only because production rises, but also because geometry favors it. At certain phase angles, forward scattering by dust can add a modest lift, making the coma and tail look richer, even if the gas flow has changed only a little. Here's a compact bundle of numbers to hold and then set down. Sunlight at Earth's distance provides about 1,060 watts per square meter. Move inward by a quarter, and the flux grows by roughly a third, giving the surface more energy to spend on sublimation. Photochemical lifetimes near this distance remain short. Hours for dicarbon, up to about a day for CN fragments. Dust grains near a micron across continue to scatter efficiently, and phase angles around 20 to 30 degrees can brighten the scene by a few tenths of a magnitude through forward scattering. Gas outflow speeds close to the nucleus hover around a mile per second, with dust launched more slowly and then bent by radiation pressure over days. As the dial turns up, expect the inner green to grow compact and slightly brighter, hugging the sunward side, where fresh molecules are made and excited first. The dust continuum will broaden, adding a warm wash that may soften the visual contrast of the green unless narrowband filters or spectra are used. The ion tail, if present, could sharpen on nights when the solar wind favors strong fluorescence, pointing almost straight away from the sun as a faint, thread-like line. A grounded speculation follows. If the nucleus hosts several stable vents rather than one dominant jet, the approach to perihelion may look like a smooth swell in both gas and dust, without sharp spikes. In such a case, the dicarbon bands should strengthen in step with CN, and the AFR proxy for dust should climb steadily. If one fissure happens to widen, a brief outburst could deepen the green for a night or two, feed extra dust into the tail, and then relax as the surface re-equilibrates. Either path fits the ordinary physics of sunlight on a modest body. Think about timing as choreography. Morning on the nucleus turns on the local flow. Noon feeds it. Evening trims it back. If the rotation period is several hours, the inner coma can show a gentle pulse, most visible in narrow slits or small apertures centered on the head. Overlaid on that pulse is the slow arc of the orbit. Near perihelion, the baseline climbs. After, it falls. The pulse rides the arc, the way a heartbeat rides a breath. Two more hard facts. Keep expectations honest. Pushing closer to the sun does not erase photochemistry. It accelerates it. Dicarbon still burns out within hours, so the green remains tight to the head even at peak. And the dust tail's curvature still records days to weeks of release, layer by layer, with the tiniest grains curving most, and the larger ones holding closer to the orbital path, like dim chalk lines. A single, vivid image to carry. Imagine a fountain in late afternoon. At the base, the water is lit a familiar green where the light is thickest. The spray arcs farther, luminous but paler, each droplet taking the hint of color only for a moment before it turns the hue of the general light. As the sun lowers, the fountain brightens briefly in the beam, then the glow eases as the angle changes. Nothing dramatic happens. The scene was always gentle. Because we are careful, we name what might mimic a peak. A run of clear, dark nights can make a steady climb look like a stronger surge. A change in phase angle can enhance the dust enough to suggest a jump in production unless spectra or narrowband photometry disentangle emission lines from continuum. Conversely, thin haze can mute violet CN and make the green seem more dominant than it is. The remedy is the same as always. Calibrate, repeat, and watch the ratios, not only the raw brightness. Here's a second compact cluster of numbers. A narrowband C2 image may require 5 to 10 minutes per exposure in small telescopes, repeated to stack cleanly. CN, near 388 nanometers, needs more time because the sky is less forgiving in the violet. Moderate resolution spectra around R, 2000 to 5000, can separate the bands from the continuum well enough to recover production rates with uncertainties of a few tenths of %. Plotting those rates against time across a fortnight around perihelion should trace a gentle hill with a width on the order of a week to two. Two steady facts keep reassurance close. The missed distance remains on the order of 200 million miles. No crest in gas output can bridge that gulf in any way that matters to safety. And the energy that powers the scene is external and self-limiting. After the crest, the same math that lifted the glow will lower it. The coma thins, the lines fade. The tail becomes a pale ledger of what the weeks have written. A small, quiet humor lives in how observers greet perihelion. There is anticipation, but it is practical. Batteries are charged, slits are aligned, filters are cleaned. People trade weather notes across longitudes so that gaps in one place are filled by clear skies in another. If a short-lived outburst occurs, someone will catch it. If not, the clean curve will be its own satisfaction. The comfort of a prediction kept. A gentle, open question is left for us to carry into the nights ahead. As the curve rises and falls, will the ratios of dicarbon to CN and the slopes of the dust continuum stay within the broad family we expect? Or will a small, persistent lean appear at the crest that points back to a slightly different pantry in a different disk long ago. The answer will not shout. It will sit in a table in round numbers next to dates and times. It'll be enough. A quiet evening, a lawn chair, and a sky that feels freshly washed. Let your eyes adapt. Then look for a soft blur that seems to hold its breath near the stars. That is all you need to begin. 2 hard facts set expectations. First, comets are extended objects, not points. So, sky darkness matters more than raw aperture. A modest pair of binoculars often reveals the coma better than a large telescope under bright suburban lights. Second, the moon is a thief of contrast. Around full phase, it will mute delicate color and swallow the faint outer coma. Plan your sessions around the darker half of the lunar month, if you can. Here is a compact bundle of numbers to hold and then let go. Under a rural sky, binoculars in the 7x50 class gather enough light for a 2 or 3 degree field and gentle hand-holding. A beginner telescope with a 4 to 6 inch mirror and a low-power eyepiece gives a field near a degree, which frames the head and the first stretch of tail. If you try photography, short exposures of 10 to 30 seconds at a fast focal ratio near f2 to f4 can capture the green head as a faint, round glow. Stack a few dozen frames, aligned on the comet's slow drift, to pull out a thin tail. Narrowband filters, centered near 530 nanometers, favor the green lines of dicarbon, and a violet filter near 388 nanometers can hint at cyanide on steady nights, though the sky is less forgiving in that band. For timing, plan on at least 20 minutes for your eyes to adjust to darkness, and leave your phone in a pocket so that you do not reset that clock. Watch how shape and brightness change over an hour. A comet's inner halo usually looks most condensed on the sunward side, with a soft gradient that rolls away from the sun. If a thin tail is present, it points roughly opposite the sun, sometimes curved, sometimes nearly straight. The green will be most compact, a small lake of color near the head. Farther out, the scene turns pale as dust takes over. If your instrument allows, tap a narrow filter into place and compare the view. The lines lift the head a little. The continuum filter makes the dust seem steadier. You are reading with 2 alphabets. 2 more hard facts help you mark the path. A comet moves against the stars, but much more slowly than a satellite. In the span of a long cup of tea, you may notice the head slide a fraction of the field. That is proper motion, and it is expected. Also, phase angle matters. When the sun, comet, and observer line up at smaller angles, forward scattering by dust can add a gentle brightening that is real and purely geometric. The green lines are different. They depend on production and photochemistry near the nucleus, so they do not rise simply because the angle is favorable. A grounded speculation follows from this. If 3IATLAS continues on a quiet, steady course, most observers will report a compact, slightly green head that brightens gradually toward and around perihelion, with the best impressions of color on moonless nights, an hour or two after dusk or before dawn. Small telescopes may reveal a short fan that rotates slowly from night to night as vents on the nucleus face the sun, while longer stacks with wide camera lenses catch a thin, pale tail several degrees long that curves gracefully into the dark. Make a small ritual of your session. Start with naked eyes to learn the neighborhood and to check for thin cloud. Sweep with binoculars, letting the coma drift into the field rather than hunting for it head on. At the telescope, use the lowest power eyepiece first. Do not chase magnification too quickly. The comet will look dimmer at high power because you are spreading the light out. If you sketch, choose a soft pencil and note the direction of the sun and the tail, the time, and the moon's phase. If you shoot, keep one run aligned on the stars for a pretty sky scene, and another aligned on the comet to measure profiles later. Both have value. One is a postcard, the other a note in the logbook. Here's a second compact cluster of numbers. If you try photometry, fixed circular apertures of 5, 10, and 15 arc seconds centered on the head are common choices. Compare your measured counts to nearby catalogued stars of known magnitude in a similar color band. Plot each night's values on a simple graph. A climb of half a magnitude over a week is meaningful for a modest comet, especially if the moon was kind and the phase angles were similar. For the dust proxy AFRAR, even rough values in the hundreds of centimeters can tell a story when you line them up night by night. A single, vivid image to keep. A faint sea urchin of light with a softer glow on one side. Hold that in the eyepiece until your brain stops asking for sharp edges. Color reveals itself best when you stop insisting it be loud. The green is most apparent when the field is dim enough and your mind lets the tint emerge like dew. Because we are careful, we name what can fool the eye. Cameras love to please. Software will happily oversaturate a green if sliders are eager. White balance can drive a neutral dust tail toward odd tones. Trust narrowband data and treat color images as illustrations unless the acquisition was designed for measurement. Also, humidity can lay a veil on the sky that steals contrast without looking like cloud. If the stars wear halos, the comet will look quieter than it should. 2 steady facts return the session to calm. Nothing about this watch makes the night unsafe. At a separation of about 200 million miles, the visitor is a study subject, not an influence, and the scene will not run away without you. If clouds win tonight, the arc of brightening and fading plays for weeks. The patient observer always gets a second chance. A small, dry humor runs through community observing. People far apart share the same quiet target, then trade notes about the one clear window between clouds and work. Someone with a small refractor under perfect darkness will see a green you cannot see from the city with a large mirror. Someone else will catch a sliver of ion tail because a breeze pushed the haze away for 10 minutes. Together, those views form a true picture. This is not a race for dramatic frames. It is a slow collage where every honest tile matters. A gentle, open question to carry outside with your jacket. As observers gather their sketches, light curves and narrow band shots, will a consistent pattern appear in which the green head rises and falls with the same easy rhythm across longitudes? Or will there be a brief, shared lift that points to a small outburst and a change in venting? Either outcome is a quiet gift. The first teaches steadiness. The second teaches texture. You can stop here and simply look. If the night is dark enough, the sky will give you a soft blur that asks very little and offers a great deal. If you choose to measure, the numbers you bring back will help others see more clearly tomorrow. Both acts belong to the same practice: attention, then patience, then meaning. Imagine a lantern set on a cold step at dusk. For a while, its glass remembers the color of the flame. Then the warmth slips away. The glass keeps the shape, but not the glow. A comet after perihelion feels like that. The chemistry that made the head green begins to quiet. The outline remains, written now in dust and light, rather than in gas and line. Two hard facts set the expectation. First, sunlight fades with distance, following a simple square rule. As 3IATLAS moves outward, the surface receives less energy. Sublimation slows, and the inner coma that fed the green contracts. Second, photochemical lifetimes for the glowing molecules grow a little longer as the ultraviolet field weakens, yet the supply falls much faster than the lifetime grows. The result is less emission, not a plateau. The green becomes a whisper near the nucleus, while the broader scene turns pale. Here is a compact bundle of numbers to hold, then let go. The solar flux near Earth is about 1,160 watts per square meter. Slide the comet to 1.5 astronomical units, and the flux is roughly 600 to 700 watts per square meter. Water-driven activity that was comfortable near perihelion can drop by a factor of a few over a couple of weeks as temperature falls. Dicarbon that glowed for hours now survives a little longer, but its formation rate collapses. Cyan fragments that lasted up to a day do not make up the difference. Ion features respond in minutes to the thinning flow and wind, and therefore fade early. Dust persists. Micron grains drift and curve for days. Larger grains keep a straighter course for weeks. The visible change is gentle. The compact green around the head loosens and dims. The dust continuum stands out, a neutral or faintly warm wash that carries the outline of a short tail. The ion tail, if it ever flashed as a thin blue thread, becomes hard to catch without deep exposures and good luck with the solar wind. To the eye and to wide field cameras, the scene looks more gray, more like breath gone to frost. A grounded speculation follows. If 3IATLAS behaves like many modest comets, the post-perihelion curve will show a soft decline in gas production and after, with small modulations tied to rotation and to the way morning and afternoon now fall on a surface that is cooling. Dicarbon will retreat to an even tighter neighborhood near the sunward edge of the head. CN may linger a touch farther out as a thin fringe, but the ratio of lines to continuum will fall. In other words, the color will not vanish in a moment. It will lose the contest with dust. Geometry keeps a hand on the dimmer. As the phase angle shifts, forward scattering weakens and then strengthens again, depending on where Earth sits in the triangle with the comet and the sun. A short, apparent flattening in the decline can appear even while production drops, a reminder that light can sweeten a curve without changing the physics. Careful observers notice these knuckles and do not mistake them for fresh vents. They check spectra or narrowband images to confirm whether lines share the lift. Two more hard facts add texture without drama. A thin dust mantle can reassert itself as gas flow wanes, closing small vents and lowering activity a little faster than sunlight alone would predict. And thermal inertia causes a lag. Surfaces warmed at perihelion do not forget overnight. The quieting arrives over several rotations, not in a single turn, as heat drains back into space and into shallow layers. There is a human-scale way to watch this with patience. In small telescopes, the 5, 10, and 15 arc-second apertures that once showed a steady climb will now begin to step down. The inner aperture will fall first and fastest as the tight green collapses. The larger apertures will follow, softened by dust that still scatters. In images aligned on the comet, profiles that look steep become flatter. The tail, once a modest arc, straightens and grows fainter, a chalk memory rather than a brushstroke. One vivid image to keep: a shoreline at ebb tide. The water pulls away, leaving damp sand that holds the shape of waves. In the last pools, you still see a hint of the sky's color, but most of the mirror is gone. The beach is not empty. It is quieter. The patterns remain. Because we are careful, we name the small ways the script can bend. A crumbly scarp might fail after perihelion, giving a one-night spike that feeds dust and gas. A glancing gust in the solar wind can tease the ion tail into view again. A change in phase angle can brighten all textures at once for a short time. None of these is a reversal. Each is a note played on a melody that is already winding down. Here's a second compact cluster of numbers. A modest decline in brightness of half a magnitude over a week is common, as a comet pulls away from 1 astronomical unit toward 1 1/4. AFR can fall from thousands of centimeters to the lower hundreds over the same span. Line fluxes for C2 drop faster than the dust continuum in many small comets by a comfortable factor, since production shuts off quickly once the thermostat passes below the waterline. Rotational modulation in small apertures can still be seen at the level of a few percent if the period is several hours. It is the pulse after the sprint. What does the fade teach? Ratios in retreat tell you about surface layering. If the green declines faster than the continuum, by more than geometry can explain, the surface may have been rich in near-surface organics that are now exhausted or hidden by a settling crust. If CN holds on a little better than C2, nitrogen-bearing parents may sit slightly deeper or survive shadow a touch longer. Either way, the shape of the step down is as informative as the height of the step up before it. Two steady facts keep reassurance at the center. The comet is still far away, on the order of hundreds of millions of miles from Earth. No change in hue alters that geometry, and the quieting is not a failure. It is the correct answer to a simple question of heat. The same physics that brought the color out now tucks it away. There is a small, dry humor in how memory works at this stage. Early images are passed around for their freshness. Late images are kept for their clarity. When the green has softened, subtraction is easier. Profiles stabilize. The numbers that describe the coma's slope and tail shape become clean pages in the logbook, even if the photographs no longer sing on their own. That too is a kind of beauty. A gentle, open question carries us forward. As 3IATLAS glides outward, will the fade trace the ordinary family curve, or will there be a second shoulder where activity persists longer than expected, hinting at a layer of ice that feels the sun a little deeper down? If a shoulder appears, will it match the rotation, the geography of a few vents that refuse to sleep? Or will it speak of thermal inertia in a crust that remembers heat for just a little longer than our models like? When green turns to gray, the lesson does not end. It becomes easier to read. The lantern is still there. It is simply letting the night say more. The eye adapts. The numbers gather. The story comes to rest without closing. Think of a wooden drawer lined with felt, not for jewelry, but for clean slips of paper. On each slip, there's a date, a time, and a few careful numbers. When a visitor like 3IATLAS fades, those slips are what remain. They're small, but they travel well. They outlast weather, headlines, and memory. Two hard facts anchor why these papers matter. First, comets teach through patterns, more than single moments. A single bright frame can be beautiful, but only a sequence tells you how gas rose and fell, how dust shifted, how ratios leaned as the sun did its steady work. Second, archived data becomes more valuable with time. 10 years from now, when a fourth or fifth interstellar visitor appears, today's numbers will be the baseline that lets us say whether the new guest belongs to a growing family or wanders at the edge. Here's a compact bundle of numbers to hold and then set down. Photometric series with fixed apertures of 5, 10, and 15 arc seconds. Around the head, let us compare inner and outer coma behavior. AFR, reported in round centimeters, gives a dust proxy that most small telescopes can track night by night. narrowband line fluxes for C2 near 520 to 560 nanometers and CN near 388 nanometers convert to production rates with tabulated efficiencies that carry uncertainties of a few tens of percent. Slit positions offset a few thousand miles from the nucleus map how lines fade with distance and help separate parent and daughter species. None of these figures needs more than a modest instrument, steady habits, and a logbook. Two more hard facts shape how we keep what we learn. Calibration is the spine. Without flats, darks, and standard stars, the prettiest image is only a picture. With them, a faint smear becomes a measurement that another observer can trust, and context belongs beside every number. Phase angle, air mass, moon fraction, filter band, and seeing conditions explain gentle bends in curves that have nothing to do with a comet at all. Good notes are an equal partner to good optics. What, precisely, do we tuck into the drawer? Light curves that show total brightness within fixed apertures. AFR, values that track dust. Spectra, or narrowband photometry, that turn green and violet into C2 and CN. Radial profiles that reveal whether the inner coma fell like gas or flattened like dust. Tail position angles that whisper how radiation pressure and orbit worked together on given nights. Occasional detections of metals, when present, as tiny flags that speak to grain history. Each item is small. Together, they form a topographic map of an apparition. A grounded speculation follows from this quiet accounting. If the record we assemble for 3IATLAS shows dicarbon and cyanide sitting in the same comfortable ranges as many modest comets, with dust slopes that behave, then a simple truth gains weight. Carbon pathways in planet-forming disks may be broadly shared. If a ratio leans, even by a modest factor, and that lean repeats across future interstellar visitors, then a second truth appears. Some nurseries stock their shelves with a slightly different balance, and our drawer becomes the catalog that proves it. There is craft in the keeping as well. Images aligned on the stars are postcards. Images aligned on the comet are measurements. Both belong in the archive, but they should be labeled plainly. Spectra need their lamps and standards noted. Photometry needs the catalog used for comparison and the method for sky subtraction. A simple habit helps. Write each observing block like a recipe card that someone else could follow years later and get the same taste. Here's a second compact cluster of numbers. For a modest campaign, 1 or 2 spectra per clear night near perihelion, plus a handful of narrowband images, can define line strengths well enough for trends. Photometry, every few nights, even if clouds intrude, draws a light curve that can be stitched with other observers' work. Uploads to public repositories within a week of observation keep the community in step and prevent numbers from hiding on a single hard drive. The Minor Planet Center accepts astrometry, AEVSO, and COBS, Welcome Comet Photometry, and NASA's Small Bodies Node preserves reduced spectra and images in long-lived formats. One vivid image to hold: a shoebox of index cards on a shelf. On the top card is a sketch of a small round head and a pale tail. Below it are tables of dates and numbers. The handwriting is steady. The edges are a little smudged from use. When the next green visitor comes, you will pull the box down, breathe the faint smell of paper, and know exactly where to look. Because we are careful, we also note what not to save as if it were gold. Saturated images that cannot be calibrated are illustrations, not measurements. Social media crops without scale bars and timestamps belong in a scrapbook, not in a dataset. Overprocessed color that pushes greens and blues beyond what filters recorded should be shared with a smile, but not cited for ratios. The archive is generous to many kinds of contribution, but it asks us to label honestly. Two steady facts reassure anyone who wonders whether a small telescope or a simple setup can help. Precision improves with repetition. 5 honest nights beat 1 perfect night if the 5 are calibrated and documented. And diversity of latitude and longitude smooths weather and geometry. A dozen observers with modest gear can outpace a single large instrument that must share its schedule and loses a week to storms. Comets reward villages. The value of the drawer does not end with science. It teaches public calm. When we can show a curve from brightening to fading, with a missed distance written clearly and no sharp turns toward risk, we help anxiety relax into attention. Numbers can be lullabies when they are paired with plain language and quiet context. A small, dry humor belongs here. The most useful files in 10 years will be the ones you named well and backed up twice. The heroic raw exposure you meant to reduce tomorrow is a ghost if it lives only in a folder called New on a laptop you no longer own. Future you is another observer. Write to them kindly. What do we keep after the green has gone? We keep ratios that sketch a birthplace. We keep dust slopes that tell us about grain sizes lifted in sunlight. We keep a simple table that lists nights when the ion tail woke or slept. We keep the dates of small outbursts, if any, and the times they faded. We keep the ephemeris used, the software version, and the calibration stars. We keep enough to repeat the math, not only to retell the story. A gentle, open question closes the box. When we place the 3IATLAS card beside 1I and 2I, will the drawer begin to show a family curve for interstellar comets, or will it remain a trio of near cousins with familiar manners and private leanings? Either way, the next time a faint green washes across a small head under a moonless sky, we will have something better than memory to guide us. We will have a map that we made together. In your mind, return to the quiet field where we began. The sky has the color of deep water. A soft tint hovers around a small traveler, as if the dark itself had learned a new word. That word has been our guide. It is time to fold it back into meaning. Two hard facts hold the center of the story. First, the green we have followed is a local light, born when sunlight excites simple molecules near the nucleus. Dicarbon sinks strongest between about 520 and 560 nanometers, close to the heart of human vision, while cyanide voices a thinner line near 388 nanometers. Both glow in the inner coma and fade within hours to a day as photochemistry breaks them. Second, distance is kindness. 3IATLAS keeps to a path about 200 million miles from Earth, a wide separation that turns color into information rather than threat. Geometry, not hope, draws that reassuring arc. Here is a compact bundle of numbers to set down and let rest. Solar flux near Earth's orbit sits near 1,360 watts per square meter, enough to warm a dusty surface to a few hundred kelvins at local noon, and to drive sublimation that lifts gas at roughly a mile per second. In that inner region, dicarbon's effective lifetime is measured in hours. Cyanide in something like a day. Dust grains near a micron across scatter efficiently and feel radiation pressure at thousandths of a G, bending a tail over days. The visitor's closest approach remains roughly 800 lunar distances away. These are round figures. They are also the quiet arithmetic of calm. Think of the script we have read. Sunlight arrives. A thin breath rises. Gas and fine dust build a small, temporary atmosphere where electrons are easy to tease. Dicarbon paints a compact green near the head. Cyanide adds a subtle fringe. Dust writes a pale sweep that curves into night. Ion features, when they show, draw a thin line straight away from the sun. All of it follows patient rules we have measured in many comets. Interstellar origin changes the postmark, not the physics of the display. Two more steady facts round the lesson. Color is not a proxy for risk. It is a proxy for composition. Green says carbon pathways are active. Violet says nitrogen joined the conversation. The strength of those notes, after dust is subtracted, tells us about parent molecules that froze long ago in a cold disk around another star. And our best assurance does not come from metaphor. It comes from ephemerides that tighten with every night of data, shrinking uncertainties to angles so small that a wide miss remains wide. A grounded speculation settles comfortably inside these facts. If 3IATLAS continues to behave like a modest, chemically ordinary comet, its ratios of dicarbon to cyanide will sit within the broad families we know from our own catalog. That would hint at a nursery where carbon-bearing ices were common and nitrogen chemistry present, but not extreme. The dust slope would lean slightly warm, as organics-coated grains so often do. Minor metal lines might whisper of silicates that once saw heat, then traveled outward to colder shelves before being ejected to interstellar space. Nothing in that picture needs drama to matter. It adds a calm page to a growing book. One vivid image to keep. Imagine a small buoy, far offshore, at night. Its lamp is not bright enough to wake a harbor, but the skin of water around it turns a particular shade for a few feet. You cannot feel that light from the beach. You can read it. You can learn something about glass and mist and distance. The buoy moves on. The lesson remains. Because we are careful, we name how worry sometimes slips into the room. Words like cyanide belong to concerns on Earth, where closed spaces and concentrations matter. In a coma at astronomical ranges, they are tracers. They survive for short times, in small amounts, and they dilute into nothing long before crossing any gulf that includes us. The green is not a cloud that can stretch across space. It is a glow that marks where electrons fell back to lower energy and sent us clean photons to measure. The watcher's part is simple and generous. Large telescopes take spectra, subtract continua, and turn band strengths into production rates with uncertainties that are honest. Small telescopes record the coma's size and brightness in fixed apertures and sketch tail angles at the edge of vision. Together, they make a thread that holds even when weather frays a night. If an outburst occurs, the thread shows a brief swell. If none does, the thread shows the quieter truth of a steady rise and fall around perihelion. Two quiet facts finish the arc. The same sun that wrote this green will erase it with equal gentleness as the traveler recedes. The coma will thin. The dust will settle into a chalk memory along the path. And the measurements we made, however modest, will be here when the next interstellar visitor appears. In that sense, a faint shade around a small stone has already done more than look pretty. It has widened our sense of what is ordinary in other systems. A gentle, open question lingers, and it belongs to the years ahead, when we place 3IATLAS on the same plot with 1I and 2I and whatever comes next. Will we see a broad overlap between visitors from other stars and comets from our own? Or will a second cloud of points gather just to one side, parallel but distinct? If a second cloud appears, will it teach us that some protoplanetary disks stock slightly different pantries of carbon and nitrogen while still playing by the same rules of light, heat, and time? Either way, the answer will be calm. It will arrive in rounded numbers and small hills on ribbons of light. So the title's question is easy to answer now. 3IATLAS is turning green because sunlight and carbon have met in a thin, local halo. Should we be worried? No. We should be attentive. We should be curious. We should be quietly pleased that a color can carry memory across millions of miles and leave it in our hands in the form of spectra, profiles, and notes. If you step outside later and the sky is kind, you might look toward the place where a soft blur moves against the stars. It will not be bright. It will be enough. You will know that the green, if you catch it, is not a warning. It is a signature. It is a last echo that ties chemistry to light and light to meaning, and meaning to rest. Let the room grow softer at the edges. Imagine space not as a black curtain, but as a slow ocean that holds small travelers lightly. One of them passed our way with a shy green near its heart. We watched. We learned. We put the learning on a small shelf where it can wait for the next time. You might picture the sun as a steady hearth and the comets as visitors who warm their hands for a few days and then continue. They leave no ash on our floor. They leave a trace only in the light that our instruments keep and in the gentle shift of perspective that arrives when distance is measured in patience. The arithmetic we use tonight is simple. Warmth falls with space. Molecules glow, then fall quiet. Dust writes a curve that time can read. These are soft rules, and they plant a soft calm. If you feel like traveling without moving, try this. Think of a round number that comforts you. 100, 1,000, 1,000,000. Let it drift outward until it becomes the miles between us and everything we have discussed. Between each number, there is more space for breath. Between each breath, there is more space for thought. The green was never coming here. It was only telling us where it was. There is a kindness in how the cosmos offers these lessons. Nothing demanded that we hurry. Nothing punished us for blinking. The glow rose, taut, and faded. It would have done the same if no one had looked. But we did look, and that is enough to make the night feel hospitable. If you wish, carry one small sentence into sleep. Color is memory made visible. When the memory fades, what remains is understanding, and understanding is gentle. You are safe. The night is wide and kind. Sweet dreams.